Hey, my name is Felipe and welcome to this fully comprehensive course on object detection. We will start by discussing what object detection is and how to measure the performance of an object detector. Then I'm going to show you a step-by-step guide on how to train your own object detector on a custom dataset, and I'm going to show you 3 different ways to detect objects on your images and videos: YOLO V8, Detectron2 and AWS Rekognition. This course is ideal for beginners as well as for more advanced developers, as it contains very valuable information and insights I gathered from years of experience as a computer vision engineer. By the end of this course, you will be familiar with different object detection algorithms and you will be able to create amazing projects using state-of-the-art computer vision technologies. And now, let's get started! So let's start with this lesson about what is object detection. I'm going to cover the definition and I'm also going to mention a few examples. So object detection is a computer vision technique to identify and locate objects within images and videos. And there are many technologies to perform object detection. These are only a few of all the available technologies, of all the available algorithms which you can use to do object detection. For example, you can use the Python library MediaPipe, which is a very popular library to do hand detection and face detection. You can also use OpenCV, which is a library available for Python and C++. You can use YOLO V8, which is the most recent version of YOLO. You can use Detectron2, which is a high-level framework based on PyTorch, and this is a very popular framework in order to do many different computer vision related tasks. You can also use AWS Rekognition, which is a service available through a cloud provider, and these are only a few of all the different ways to do object detection, and there are many ways, and I don't know how many ways to do object detection. These are only a few of them. And although there are many algorithms and many technologies, all of them work pretty much the same from a high-level perspective, from an input-output perspective. All of them receive an image as input, and the output is a list of all the detected objects in that image. And the objects in that image are given by these 3 values: the bounding box, which is the location of the object in the image, then the confidence score, which is a value from 0 to 1, and it means how confident the object detector is regarding that detection, and then the object category or the class name, right? Because if we have detected an object, we want to know what object we have detected, right? We want to know the name of that object. So pretty much all the object detectors work pretty much the same way, and they are going to return something which looks like this. The bounding box is usually specified with 4 values, and there are many different formats, many different conventions in order to specify the bounding box, and this is one of the most popular formats in order to do so, which is the X and Y position of the top left corner and then the X, Y position of the bottom right corner, right? With these 2 values, with these 2 corners, then we have specified the bounding box, and then the confidence score, and then the class name. So remember, although there are many ways to do object detection, they all work pretty much the same way from an input-output perspective. And this is a very specific example of how to do object detection in this image. You can see that this is the image of a cat and a dog, and this is a Python script, a very simple Python script which uses YOLO V8 in order to detect all the objects within this image. And I'm not going into the details of how this script works, but this is going to be available in the GitHub repository of this tutorial. So if we execute this script, you can see that at the end we are iterating in all the detections we have detected in this image, and we are printing all the detections. And if we execute this script, we are going to print something like this. You can see that we have detected a cat. This is the bounding box where the cat is located, and this is the confidence score of the object detector regarding this detection. And then we have also detected a dog. This is the bounding box of the dog, and this is how confident the object detector is regarding this detection. So this is a very simple example of how object detection works on a very specific image, and this is going to be pretty much all for this lesson. So remember, object detection is a technique, a computer vision technique technique to identify and locate all the objects within an image or a video, and although there are many different ways to do object detection, all of them work pretty much the same from an input-output perspective. Now let's move to the next lesson about object detection metrics. So let's talk about object detection metrics. We will answer the question how to measure the performance of an object detector. And you can see that we are just starting with this lesson and we immediately got this huge warning sign which says when using object detection metrics you are only comparing your predictions with your ground truth. This is very important and you're going to see exactly why later on this lesson. But for now let's continue. So this is the roadmap we will be covering today. I have divided all the content in this lesson into two sections. The first one is about fundamentals, and this is where we will discuss all the definitions of all the metrics we will be using today, all the different examples I'm going to show you about these metrics, and we will assume we are working under ideal conditions, and this is very important, and you're going to see exactly what I mean with ideal conditions later on. And then we have the other section, which is the one for the more advanced topics, and this is where we will assume real life conditions. For now, let's continue. So let's start with the fundamentals. We are going to cover the most common metrics and we will assume the data we are using to train the model is perfect. This is what I meant with ideal conditions, right? We will assume our dataset is perfect, which involves we have many samples, we have a huge dataset, and in case we have many different classes in our dataset, we will assume this is all of our classes are equally distributed, which means we have the same amount of objects for each one of our classes, but most importantly, we will assume our dataset is perfectly annotated. So we have no issue in our dataset whatsoever, right? These are the ideal conditions we will be assuming in this section. Now let's continue. These are the most common metrics which are commonly used in object detection. So we have the loss function, which is used during the training process, and then we have these two other metrics which are part of the evaluation process of an object detector, which are the intersection over union and the mean average precision. Now let me show you a very specific example of how this looks like on real life, right? Remember from our previous lesson I told you there were many different ways to do object detection, many different technologies, many different algorithms. Now YOLO V8 is only one of all the different options of doing object detection, and when training a model with YOLO V8, this is what we got at the end of the training process. At the end of the training process, we will have all these many plots, so we can analyze the training process itself, and we can also analyze the performance of the object detector we have just trained. And from all of these plots, you can see that 6 of them are related to the loss function. And I'm not going into the details on why we have so many plots for the loss function, but just keep in mind that this is such an important metric that we have all these many plots in order to analyze the performance of the model and the performance of the training process regarding the loss function. This is such an important metric that is why we have so many plots. And then the remaining 4 plots are related to the mean average precision. And in the case of YOLO V8, in the case of training an object detector with YOLO V8, the intersection over union is not provided, but this is also a very important metric in object detection. Now let's continue. Let's start with the loss function. This metric is related to the learning process, to the training process. And there are different loss functions, there are many loss functions, and they usually involve very complex mathematical expressions. Very complex mathematical formulations and expressions. And the only thing I'm going to cover in this course about object detection is that regarding the loss function, lower is better. So a lower value of the loss function means it's better. And if we go back to these plots we have over here, you can see that in all of these plots regarding the loss function, in all of them, you can see that the loss function is going down as we increase the number of epochs, right? So this is the only thing I want you to remember for now. The loss function is related to the learning process. They usually involve very complex and very advanced mathematical expressions, and lower is better. Now let's continue. Let's move on to the intersection over union, and this metric measures the detection accuracy. It ranges between 0 and 1, so the intersection over union is a value between 0 and 1, and higher is better. And this is exactly how the intersection over union is computed. So we have the given two bounding boxes, right? Remember, we are going to be comparing our detections with the ground truth. So we will have a bounding box for our detections, and we will have a bounding box for the ground truth. Given these two bounding boxes, we will measure the area of overlapping, and we will measure the area of union, and then we will just compute the intersection over union, making this very simple calculation, right? Let me show you an example. So we have these two pictures of a cat. We have a cat in each one of these pictures, and this, you can assume these are the ground truth bounding boxes for these objects, right? You can see in each case this is a bounding box which encloses the object perfectly. This is the ground truth. Now let's assume we are using an object detector, and these are the detections we got with our object detector. And now let's assume we want to compute the intersection over union for each one of these cases. In the case of this example over here, we have a very small intersection. We have a very small overlapping. So if we apply this formula we have over here, which is the area of overlapping, over the area of union, we will have a very low value, and this value is 0.15, right? So in this case we have a very small value because these two bounding boxes have a very small area of overlapping, of intersection. But in the other case, you can see that our prediction is very close to the ground truth, right? It's almost perfectly matching the ground truth. So in this case we will have a higher value of intersection over union, and in this case is 0.95. So this is a very simple example for you to get like a much better idea regarding the intersection over union. Now let's continue. Let's move to the mean average precision. The mean average precision is based on the precision recall curve, and the precision recall curve is based on the intersection over union and the detection confidence score, right? Remember from our previous lesson on what is object detection, remember I mentioned that all of the different frameworks, all of the different algorithms in order to do object detection, all of them have pretty much the same structure regarding the input-output, and the output will always involve a bounding box and also a confidence score. So the precision recall curve is based on the intersection over union and the detection confidence score. The recall measures how effectively we can find objects, right? From the precision recall curve, we have two elements. One of them is precision, the other one is recall, and the recall measures how effectively we can find objects. And then precision measures how well we perform once we find an object. Please mind these two definitions. Please mind the difference between these two definitions. This is very important, and this is going to be much more clear in a few minutes because I'm going to show you a few examples. But please focus on each one of these two definitions, on how we are defining recall and how we are defining precision. And then about the mean average precision, remember that higher is better. Now let's move on. Now it's where we are going to describe an example on how to compute the mean average precision. So this is our dataset, right? Let's assume that we have 10 apples in our dataset, and for each one of these apples, for each one of these objects, we have the ground truth, right? We have a bounding box which encloses the object perfectly, right? So this is our data, and these are our annotations. This is our ground truth. Now let's assume we are working with an object detector, and these are our detections, right? In some cases, for example here or here or here, we are getting like an okay detection, but in other cases like here or here, we are not getting a very good detection, right? So let's see how we can compute the mean average precision in this example. So this is the ground truth with the predictions on top. Now we are visualizing both the predictions and the ground truth, and these are some values which are going to be super important in order to compute the mean average precision. You can see that for each one of these objects we have two values. The score, which is the confidence score of that prediction, right? It's the confidence score of the green bounding box, and then the intersection over union, which is the intersection over union between the green bounding box and the blue bounding box. It's the intersection over union between our prediction and the ground truth. You can see that for each object in our dataset, we have these two values, the confidence score of the green bounding box and the intersection error union between the green bounding box and the blue bounding box. And what we will be doing now is we will be applying this very simple process. This is pseudo code. This is not real code, right? This looks like Python, but it's not really Python. This is the pseudo code of the process we will follow in order to compute the mean average precision. Please mind and please pay attention because this is very important. You can see that we are defining a variable which is intersection error union threshold, and we are defining this variable as 0.5. Then we are iterating in many different values for the confidence score threshold, and we are defining two variables. For each one of these iterations, we are defining two variables which are true positives and false positives, and we are initializing each one of these variables in 0. Then for each one of our detections, for each one of our green bounding boxes, we are going to verify if the confidence score we got is greater than the confidence score threshold we are computing in this iteration. And if it is greater than this confidence score threshold, we will take a look at the intersection over union between the green bounding box and the blue bounding box. And if this is greater than the intersection over union threshold, then we are going to increment the true positives variable, and in your case, we are going to increment the false positives variable. So this is a very simple and a very straightforward process in order to compute the mean average precision, but please focus on this process. Please go through this process more than once. Please be super clear on how this works, because it's very important to understand how this process works. So once we have computed the true positives and the false positives, right? Remember that for each one of the values in confidence score threshold, we will be computing the true positives and the two false positives. We will be computing these two variables. Once we have computed these two variables, we are going to define precision and recall exactly like this. Precision will be the true positives divided by the number of true positives plus false positives, and in case of recall, we will be dividing the true positives for the total number of ground truth objects. And in our case, the total number of ground truth objects is 10, right? Remember, we have 10 blue bounding boxes, and that's exactly our ground truth. So in our case, this number will always be 10. Now let's continue. So let's go through this iteration, let's go through this process once and again, and let's start with a confidence score threshold of 0.75, right? In order to do so, we are going to go through each one of these green bounding boxes. We're going to go through each one of our detections, and we are going to keep only the ones which have a confidence score greater than 0.75, which are these three bounding boxes, right? If we go back, you can see that in this case, the confidence score is 0.7, in this case it's 0.4, 0.2, and so on. In all the other bounding boxes, the confidence score is lower than our threshold of 0.75. And we are going to take a look at the intersection over union, and in case the intersection over union is greater than the threshold we have defined of 0.5, then we are going to increment the true positives, and if it's not greater, if it's lower than 0.5, we are going to increment the false positives. And in this case, you can see that the intersection over union is 0.85, so this is greater than 0.5, so this is a true positive. This is also 0.85, so this is also greater than 0.5, so this is also a true positive. And in this case, this is also a true positive because the intersection over union is 0.8. So in this case, we have 3 true positives and we have 0 false positives. If we move here, you can see that this is exactly what we have just mentioned. The true positives is 3, the false positives is 0. So if we compute precision and recall, we get that precision is 1 and recall is 0.3. Right? It's a very simple process, a very straightforward process. Please go through this example once and again until you are completely and 100% clear on what we are doing, because once you get familiar with the process, it's very simple. But now let's move on to a confidence score threshold of 0.5. In this case, we are going to do exactly the same. We are going to filter all the detections with a confidence score lower than 0.5, and this is what we got. And now let's go through each one of these detections and let's see if the intersection error union is greater or lower than 0.5. In this case, it's greater than 0.5, so this is a true positive, this is also a true positive, also a true positive, this is also a true positive, this is also a true positive, but in this case, the intersection error union is 0.4, which is lower than 0.5, so this is a false positive. So we have 5 true positives and only 1 false positive, and if we compute the precision on recall, we got that precision is 0.83 and recall is 0.5, right? Let's continue. Now let's move to confidence score threshold equal to 0.25. We're going to filter all the detections with a confidence score lower than 0.25. This is what we got. And let's take a look at the intersection error union. You can see in this case, true positive, true positive, true positive. In this case, it's 0.1, so this is a false positive. This is also a true positive, and this is a false positive, and this is also a true positive. So we have 1, 2, 3, 4, 5, 6 true positives and 2 false positives. And this is what we have over here. We have 6 true positives, 2 false positives, and the precision is 0.75 and the recall is 0.6. Now let's continue. Now let's compute exactly the same values but for a confidence score threshold of 0. In this case, we are not going to filter any detection because all of them have a confidence score which is greater than 0. And in this case, you can see that this is a true positive, true positive, true positive. This is a false positive, this is a true positive. This is also a false positive, and then all the other ones are true positives except this one, which is a false positive. So we have 1, 2, 3, 4, 5, 6, 7 true positives and only 3 false positives, and this is exactly what we have over here. So the precision is 0.7 and the recall is 0.7. So we have computed all these different values for precision and recall, and from here is super easy and super straightforward to put everything together under a precision recall curve, right? We can very easily to take all these pairs of values of precision and recall and to put everything together on a plot which looks like this, right? And if we compute the area under the curve, we will be computing the average precision, which is a very important value we need to compute before computing the mean average precision. And please do the math yourself, and if I'm mistaken, please let me know in the comments below, but if I'm not mistaken, this is the value I have computed for this curve we have over here. And a very quick note is that as we were using an intersection error union threshold of 0.50, this is sometimes referred to as average precision at 50, right? If you search for the literature, or if you search for other blogs or YouTube videos and so on, if you search for other places in which they talk about the average precision or the mean average precision, you will find that sometimes this value is referred to as average precision at 50, and we can also compute other values. For example, if we were using an intersection error union threshold of, for example, 0.90, then this will be the average precision at 90, right? This is a very quick note, but for now, let's just continue. So we have computed the average precision, and from here, if we want to compute the mean average precision, the only thing we need to do is a very simple calculation, because in our case, we are working with only one class, right? We are detecting apples and we are working with only one class, which is apple. But in the most generic case, you will be computing the average precision for many different classes, right? So in the most generic case, the mean average precision will look something like this, right? You will have many different average precision values for each one of your classes, and then in order to compute the mean average precision, the only thing you need to do is to sum everything together and to take the average, right? That's exactly how you can compute the mean average precision, and remember, in our case, we are always working with an intersection error union threshold of 0.50. As we are using only one value for the intersection error union threshold, this is exactly how the mean average precision looks like in our case. Now, let's continue. This is your homework. This is your homework from this tutorial. Now, tell me which model performs better. We have 2 models, and for each one of these models, we have the intersection error union and we also have the mean average precision, right? the intersection reunion of the model A is 0.70 and the mean average precision is 0.80, and for the model B the intersection reunion is 0.55 and the mean average precision is 0.72. Now your homework from this video is to tell me which model performs better. So let me know in the comments below if you find the answer to this question, and I will be super happy to read your answer in the comments below. And if you don't know which model performs better, then also let me know in the comments below, and I will be super happy to help you, or maybe another member in our community will be super happy to help you as well. But this is going to be all for this section, for the fundamentals, and now let's move to the more advanced section. This is where we are going to work with imperfect data, right? This is where we are going to have a dataset which is going to comply with one of the following sentences. Maybe we don't have enough samples, maybe we are working with a very small dataset, maybe we have an unbalanced dataset, which means we have many different classes and we don't have the same amount of objects for all of our classes, or maybe most importantly we have errors in our annotations, right? If you have one or more than one of these issues in your dataset, this is where it's super important to remember we are comparing the detections against the ground truth, right? All of the metrics we have mentioned so far, the only thing we're doing is comparing the detections against the ground truth. This is where it's super important to remember the warning we got when we were starting this lesson. So if we are in this situation, I want you to take your performance metrics with a grain of salt, which means compute everything you want to compute the intersection reunion, please compute the mean average precision, all your losses, compute every single metric you want, but please take all of your metrics with a grain of salt. And a very good example of this situation is one of my previous tutorials where I show you how to train a semantic segmentation model using YOLO V8. This previous tutorial was not really about object detection, but this was about semantic segmentation, but I think it's a very good example nevertheless. In this previous tutorial we had a ground truth, we have a data set which had many different errors, and in this previous tutorial we noticed that the detections we got with the model we trained were even better than the data we used to train the model, were even better than the ground truth. So this is a very good example of what happens in a situation like this, right? This is a very good example of a situation in which we have many issues in our data and we have to be super cautious in the way we interpret, in the way we read, in the way we make sense of the object detection metrics, right? Now I'm not going to show you the entire previous tutorial on semantic segmentation using YOLO V8, but let's just remember a few minutes from this previous tutorial, those few minutes where we noticed we had an issue with our data and we noticed that the predictions we got with our model were even better than the data we used to train this model. Let's remember these few minutes. And then, in order to continue with this process, with this validation, is that we are going to take a look at what happens with our predictions. How is this model performing with some data, with some predictions? And for this, we are going to take a look at what happens with all of these images, right? You can see that these are some badges, and these are some of our labels, some of our annotations for all of these images, and then these are some of the predictions for these images, right? So we are going to take a look at what happens here, and for example I'm going to show you this result, the first image, and you can see that looking at this image, which again these are not our predictions, but this is our data, this is our annotations, these are our labels, you can see that there are many missing annotations. For example, in this image we only have one mask, we only have the mask for one of our dogs. We have 1, 2, 3, 4, 5 dogs, but only one of them is annotated. We have a similar behavior here, only one of the dogs is annotated. Here is something similar, only one of them is annotated. And the same happens for absolutely every single one of these images. So there are a lot of missing annotations in this data we are currently looking at. And if I look at the predictions, now these are the same images, but these are our predictions, we can see that nevertheless we had a lot of missing annotations. The predictions don't really look that bad, right? For example, in this case, we are detecting 1, 2, 3 of the 5 dogs, so we have an even better prediction that we had over here. I would say it's not a perfect detection, but I would say it's very good, right? It's like, it's not 100% accurate, but it's like very good. And I would say it's definitely better than the data we used to train this model. So that's what happens with the first image, and if I take a look at the other images, I can see a similar behavior, right? This is the data we use for training this algorithm, and this is the predictions we got for these images, and so on, right? It seems it's like this, exactly the same behavior, exactly the same situation for this image as well. So my conclusions by looking at these images, by looking at these predictions, is that the model is not perfect, but I would say performs very well, especially considering that the data we are using to train this model seems to be not perfect, seems to have a lot of missing detections, have a lot of missing elements, right? A lot of missing objects. So that's our conclusion. That's my conclusion by looking at these results, and that's another reason for which I don't recommend you to go crazy analyzing these plots. Because when you are analyzing these plots, remember, the only thing you're doing is that you are comparing your data, the data you are using in order to train this model, with your predictions, right? The only thing you're doing is you're comparing your data with your predictions, with the predictions you got with the model, right? So as the only thing you're doing is a comparison between these two things, then if you have many missing detections or many missing objects, or if you have many different errors in your data, in the data you're using to train the algorithm, then this comparison, it's a little meaningless, right? It doesn't really make a lot of sense, because if you're just comparing one thing against the other, but the thing you are comparing with, it has a lot of errors, it has a lot of missing objects and so on, maybe the comparison doesn't make a lot of sense whatsoever, right? That's why I also recommend you to not go crazy when you are analyzing these plots, because they are going to give you a lot of information, but you are going to have even more information when you are analyzing all of these results. And this is a very good example of what happens in real life when you are training a model in a real project. Because remember that building an entire dataset, a dataset which is 100% clean and absolutely 100% perfect, is very expensive. So this is a very good example of what happens in real life. Usually the data you're using to train the model, to train the algorithm, has a few errors. And sometimes there are many errors. So this is a very good example of how this validation process looks like with a data which is very similar to the data we have in real life, which in most cases is not perfect. And obviously you are more than welcome to watch the entire tutorial after you complete this course. For now, let's just move to the next video where I'm going to show you how to train an object detector on your own custom data. Hey, my name is Felipe and welcome to my channel. In this video we are going to train an object detector using YOLO V8, and I am going to walk you step by step through the entire process, from how to collect the data you need in order to train an object detector, how to annotate the data using a computer vision annotation tool, how to structure the data into the exact format you need in order to use YOLO V8, how to do the training, and I'm going to show you 2 different ways to do it, from your local environment and also from a Google Colab, and how to test the performance of the model you trained. So this is going to be a super comprehensive step-by-step guide of everything you need to know in order to train an object detector using YOLO V8 on your own custom dataset. So let's get started. So let's start with today's tutorial, let's start with this process, and the first thing we need to do is to collect data. The data collection is the first step in this process. Remember that if you want to train an object detector or any type of machine learning model, you definitely need data. The algorithm, the specific algorithm you're going to use, in this case YOLO V8, is very important, but the data is as important as the algorithm. If you don't have data, you cannot train any machine learning model. That's very important. So let me show you the data I am going to use in this process. These are some images I have downloaded and which I'm going to use in order to train this object detector, and let me show you a few of them. These are some images of alpacas. This is an alpaca dataset I have downloaded for today's tutorial, and you can see these are all images containing alpacas in different postures and in different situations, right? So this is exactly the data I am going to use in this process, but obviously you could use whatever dataset you want. You could use exactly the same dataset I am going to use, or you can just collect the data yourself. You could just take your cell phone or your camera or whatever, and you can just take the pictures, the photos, the images you are going to use. You can just do your own data collection. Or something else you could do is to just use a publicly available dataset. So let me show you this dataset. This is the OpenImages dataset version 7, and this is a dataset which is publicly available, and you can definitely use it in order to work on today's tutorial, in order to train the object detector we are going to train on today's tutorial. So let me show you how it looks like. If I go to Explore and I select Detection, you can see that I'm going to unselect all these options. You can see that this is a huge dataset containing many categories. I don't know how many, but they are many. This is a huge dataset. It contains millions of images, hundreds of thousands, if not millions of annotations, thousands of categories. This is a super huge dataset, and you can see that you have many different categories. Now we are looking at trumpet, and you can see these are different images with trumpets, and from each one of these images we have a bounding box around the trumpet. And if I show you another one, for example, we also have beetle. And in this category, you can see we have many different images from many different type of beetles. So this is another example. Or if I show you this one, which is bottle, and we have many different images containing bottles. For example, there you can see many different type of bottles, and in all cases we have a bounding box around the bottle. And I could show you, I don't know how many examples, because there are many different categories. So remember, the first step in this process is the data collection. This is the data I am going to use in this project, which is a dataset of alpacas. And you can use the exact same data I am using. If you want to, you can use the same dataset of alpacas, or you can just collect your own dataset by using your cell phone, your camera, or something like that. Or you can also download the images from a publicly available dataset, for example, OpenImages dataset version 7. If you decide to use OpenImages dataset version 7, let me show you another category, which is alpaca. This is exactly from where I have downloaded all of the images of alpacas. So if in case you decide to use this publicly available dataset, I can provide you with a couple of scripts I have used in order to download all this data, and in order to parse through all the different annotations and through to format this data in the exact format we need in order to work on today's tutorial. So in case you decide to use OpenImages dataset, I am going to give you a couple of scripts which are going to be super useful for you. So that's all I can say about the data collection. Remember, you need to collect data if you want to train an object detector, and you have all those different ways to do it, and all these different categories and all these different options. So now let's move on to the next step. And now let's continue with the data annotation. You have collected a lot of images, as I have over here. You have a lot of images which you have collected yourself, or maybe you have downloaded this data from a publicly available dataset, and now it's the time to annotate this dataset. Maybe you were lucky enough when you were creating the dataset, and maybe this dataset you are using is already annotated. Maybe you already have all the bounding boxes from all of your objects, from all your categories. Maybe that's the case. So you don't really need to annotate your data. But in any other case, for example, if you were using a custom dataset, a dataset you have collected yourself with your own cell phone, your camera, and so on, something you have collected, in that case, you definitely need to annotate your data. So in order to make this process more comprehensive, and in order to show you like the entire process, let me show you as well how to annotate data. So we are going to use this tool, which is CBAT. This is a labeling tool. I have used it many times in many projects. I would say it's one of my favorite tools. I have used pretty much absolutely all the object detection, computer vision related annotation tools I have used. Maybe I haven't used them all, but I have used many of them. And if you're familiar with annotation tools, you would know that There are many of them and none of them is perfect. I will say all of the different annotation tools have their advantages and their disadvantages, and for some situations you prefer to use one of them, and for other situations it's better to use another one. CBIT has many advantages and it also has a few disadvantages. I'm not saying it's perfect, but nevertheless this is a tool I have used in many projects and I really like it. So let me show you how to use it. You have to go to cbit.ai and then you select try for free. There are different pricing options, but if you're going to work on your own or in a very small team, you can definitely use the free version. So I have already logged in. This is already logged into my account, but if you don't have an account, then you will have to create a new one. And yeah, so you're going to see like a sign up page, and you can just create a new account, and then you can just log into that account. So once you are logged into this annotation tool, you need to go to projects and then create a new one. I'm going to create a project which is called Alpaca Detector, because this is a project I am going to be working in, and I'm going to add a label, which in my case is going to be only one label, which is Alpaca. And then that's pretty much all. Submit and open. I have created the project. It has one label, which is Alpaca. Remember, if your project has many different labels, add all the labels you need. And then I will go here, which is create a new task. I am going to create a new annotation task, and I'm going to call this task something like Alpaca Detector Annotation Task 001. This is from the project Alpaca Detector, and this will take all the labels from that project. Now you need to upload all the images you are going to annotate. So in my case, I'm obviously not going to annotate all the images, because you can see these are too many images and it doesn't make any sense to annotate all these images in this video. These are 452 images, so I'm not going to annotate them all, but I'm going to select a few in order to show you how exactly this annotation tool works and how exactly you can use it in your project. Also, in my case, as I have downloaded these images from a publicly available dataset, from the Open Images dataset version 7, I already have the annotations. I already have all the bounding boxes. So in my case, I don't really need to annotate this data because I already have the annotations, but I'm going to pretend I don't. So I can just label a few images and I can show you how it works. So now I go back here and I'm just going to select something like this many images, right? Yeah, I'm just going to select these many images. I'm going to open these images, and then I'm going to click on submit and open, right? So this is going to create this task, and at the same time it's going to open this task so we can start working on our annotation process. Okay, so this is the task I have just created. I'm going to click here in job number and the job number, and this will open all the images, and now I'm going to start annotating all these images. So we are working on an object detection problem, so we are going to annotate bounding boxes. We need to go here, and for example, if we will be detecting many different categories, we will select what's the category we are going to label now, and that's it. In my case, I'm going to label always the same category, which is alpaca, so I don't really need to do anything here. So I'm going to select shape, and let me show you how I do it. I'm going to click in the upper left corner and then in the bottom right corner. So the idea is to enclose the object and only the object, right? The idea is to draw a bounding box around the object and anywhere else, right? You only want to enclose this object. And you can see that we have other animals in the back, right? We have other alpacas, so I'm just going to label them too. And there is a shortcut which is pressing the letter N, and you can just create a new bounding box. So that's another one, this is another one, this is another alpaca, and this is the last one. Okay. That's pretty much all. So once you're ready, you can just press Ctrl S. That's going to save the annotations. I recommend you to press Ctrl S as often as possible because it's always a good practice. So now everything is saved. I can just continue to the next image. Now I'm going to annotate this alpaca, and I'm going to do exactly the same process. I can start here, obviously. You can just start in whatever corner you want, and I'm going to do something like this. Okay. this image is completely annotated. I'm going to continue to the next image. In this case, I'm going to annotate this alpaca too. This is not a real alpaca, but I want my object detector to be able to detect this type of objects too. So I'm going to annotate it as well. This is going to be a very good exercise because if you want to work as a machine learning engineer or as a computer vision engineer, annotating data is something you have to do very often, or actually training machine learning models is something you have to do very often. So usually the data annotation is done by other people, right? It's done by annotators, it's done by, I don't know, there are different services you can hire in order to annotate data. But in whatever case, whatever service you use, it's always a very good practice to annotate some of the images yourself, right? Because if you annotate some of the images yourself, you are going to be more familiar with the data, and you're also going to be more familiar on how to instruct the annotators on how to annotate this particular data. For example, in this case, it's not really challenging. We just have to annotate these two objects, but let me show you. There will be other cases because there will be always situations which are a little confusing. In this case, it's not confusing either. I have just to label that object. But for example, a few images ago when we were annotating this image, if an annotator is working on this image, that person is going to ask you, what do I do here? Should I annotate this image or not? Right? If an annotator is working on this image and the instructions you provide, they are not clear enough, this person is going to ask you, hey, what do I do here? Should I annotate this image or not? Is this an alpaca or not? So, for example, that situation, another situation will be what happened here, which we had many different alpacas in the background, and some of them, for example, this one is a little occluded. So there could be an annotator, someone who asks you, hey, do you want me to annotate absolutely every single alpaca, or maybe I can just draw a huge bounding box here in the background and just say everything in the background is an alpaca. Something like that. When an annotator is working on the images, they are going to have many different questions regarding how to annotate the data, and they are all perfect questions and very good questions because this is exactly what's about. I mean, when you are annotating data, you are defining exactly what are the objects you are going to detect, right? So what I'm going is that if you annotate some of the images yourself, you are going to be more familiar on what are all the different situations, on what exactly is going on with your data, so you are more clear in exactly what are the objects you want to detect, right? So let's continue. This is only to show a few examples. This is another situation. In my case, I want to say that both of them are alpacas, so I'm just going to say something like this. But there could be another person who says, no, this is only one annotation, it's something like this, right? I'm just going to draw one bounding box enclosing both of them, something like that. And it will be a good criteria. I mean, it will be a criteria, which I guess it will be fine. But whatever your criteria would be, you need one, right? You need a criteria. So while you are annotating some of the images, is that you are going to further understand what exactly is an alpaca, what exactly is the object you want to consider as alpaca. So I'm just going to continue. This is another case which may not be clear, but I'm just going to say this is an alpaca, this black one, which we can only see this part and we don't really see the head, but I'm going to see it. I'm going to say it's an alpaca anyway. This one too, this one too, this one too. Also, this is something that always happens to me when I am working, when I am annotating images, that I am more aware of all the diversity of all these images. For example, this is a perfect example because we have an alpaca which is being reflected on a mirror, and it's only like a very small section of the alpaca. It's only like a very small piece of the alpaca's face. So what do we do here? I am going to annotate this one too, because yeah, that's my criteria. But another person could say, no, this is not the object I want to detect. This is only the object I want to detect. And maybe another person will say, no, this is not an alpaca. Alpacas don't really apply makeup on them. This is not real, so I'm not going to annotate this image. You get the idea, right? There could be many different situations, and the only way you get familiar with all the different type of situations is if you annotate some images yourself. So now let's continue. In my case, I'm going to do something like this, because yeah, I will say the most important object is this one, and the other ones are like, yeah, it's not really that important if we detect them or not. Okay, so let's continue. This is very similar to another image. I don't know how many I have selected, but I think we have only a few left. I don't know if these type of animals, they are like natural. I'm very surprised about this, like the head, right? It's like it has a lot of hair over here, and then it's completely hairless, the entire body. I mean, I don't know, I'm surprised. Maybe they are made like that, or maybe it's like a natural alpaca. Who cares? Let's continue. So we have, let's see how many. We have only a few left, so let's continue. Let's see if we find any other strange situation which we have to define if that's an alpaca or not, so I can show you an additional example. Also, when you are annotating, you could define your bounding box in many different ways. For example, in this case, we could define it like this. We could define it like this. I mean, we could define it super fit to the object, something like this, super fit, and we could enclose exactly the object, or we could be a little more relaxed, right? For example, something like this will be okay too, and if we want to do it like this, it will be okay too, right? You don't have to be super accurate. You could be like a little more relaxed, and it's going to work anyway. Now in this last one, and that's pretty much all. This is the last one. Okay, I'm going to do something like this. No, I'm going to do it like this. I think this is also alpaca, but anyway, I'm just going to annotate this part. So that's pretty much all. I'm going to save, and those are the few images I have selected in order to show you how to use this annotation tool. So that's pretty much all for the data annotation. And remember, this is also a very important step. This is a very important task in this process, because if we want to train an object detector, we need data and we need annotated data. So this is a very important part in this process. Remember this tool, CBAT. This is only one of the many available image annotation tools. You can definitely use another one if you want. It's perfectly fine. It's not like you have to use this one at all. You can use whatever annotation tool you want, but this is a tool I think it's very easy to use. I like the fact it's very easy to use. It's also a web application, so you don't really need to download anything to your computer. You can just go ahead and use it from the web. That's also one of its advantages. So yeah, so this is the tool I show you in this video how to use in order to train this object detector. So this is going to be all for this step, and now let's continue with the next part in this process. And now that we have collected and annotated all of our data, now it comes the time to format this data, to structure this data into the format we need in order to train an object detector using YOLO V8. When you're working in machine learning and you're training a machine learning model, every single algorithm you work with, it's going to have its own requirements on how to input the data. That's going to happen with absolutely every single algorithm you will work with. It's going to happen with YOLO, with all the different YOLO versions, and it's going to happen with absolutely every single algorithm you are working with. So specifically, YOLO V8 needs the data in a very specific format. So I created this step in this process so we can just take all the data we have generated, all the images and all the annotations, and we can convert all these images into the format we need in order to input this data into YOLO V8. So let me show you exactly how we are going to do that. If you have annotated the data using CBAT, you have to go to Tasks, and then you have to select this option, and it's Export Task Dataset. It's going to ask you the export format, so you can export this data into many different formats, and you're going to scroll all the way down, and you're going to choose YOLO 1.1, right? Then you can also save the images, but in this case not really needed. We don't really need the images, we already have the images, and you're just going to click OK. Now, if you wait a few seconds or a few minutes, if you have a very large data set, you are going to download a file like this. And if I open this file, you're going to see all these different files, right? You can see we have 4 different files, or actually 3 files and a directory. And if I open the directory, this is what you are going to see, which is many different file names. And if I go back to the images directory, you will see that all these images file names, they all look pretty much the same, right? You can see that the file name, the structure for this file name looks pretty much the same as the ones we have just downloaded from CBAT. So basically the way it works is that when you are downloading this data into this format, into the YOLO format, every single annotation file is going to be downloaded with the same name as the image you have annotated, but with a different extension. So if you had an image which was called something.jpg, then the annotation file for that specific image will be something.txt, right? So that's the way it works. And if I open this image, you are going to see something like this. You're going to see, in this case, only one row, but let me show you another one which contains more than one annotation. I remember there were many, for example, this one, which contains 2 different rows, and each one of these rows is a different object. In my case, as I only have alpacas in this dataset, each one of these rows is a different alpaca, and this is how you can make sense of this information. The first character is the class you are detecting. I wanted to enlarge the entire file, and I don't know what I'm doing. There, okay. Okay, the first number is the class you are detecting. In my case, I only have one, so it's only a 0 because it's my only class. And then these 4 numbers which define the bounding box, right? This is encoded in the YOLO format, which means that the first 2 numbers are the position of the center or of the bounding box. Then you have the width of your bounding box and then the height of your bounding box. This, you will notice, these are all float numbers. And this basically means that it's relative to the entire size of the image. So these are the annotations we have downloaded, and this is in the exact same format we need in order to train this object detector. So remember, when I was downloading these annotations, we noticed there were many different options. All of these different options are different formats in which we could save the annotations. And this is very important because you definitely need to download YOLO, because we are going to work with YOLO, and everything is pretty much ready as we need it in order to input into YOLO V8, right? If you select YOLO, that's exactly the same format you need in order to continue with the next steps. And if you have your data into a different format, maybe if you have already collected and annotated your data and you have your data in whatever other format, please remember you will need to convert these images, or actually to convert these annotations into the YOLO format. Now, this is one of the things we need for the data. This is one of the things we need in order to, we need to format in order to structure the data in a way we can use this object detector with YOLO V8. But another thing we should do is to create very specific directories containing this data, right? We are going to need 2 directories. One of them should be called images and the other one should be called labels. You definitely need to input these names. You cannot choose whatever name you want. You need to choose these 2 names, right? The images should be located in a directory called images, and the labels should be located in a directory called labels. That's the way YOLO V8 works. So you need to create these 2 directories. Within your images directory is where we are going to have your images. If I click here, you can see that these are all my images. They are all within the images directory. They are all within the train directory, which is within the images directory. This directory is not absolutely needed, right? You could perfectly take all your images, all these images, and you could just paste all your images here, right in the images directory, and everything will be just fine. But if you want, you could do something exactly as I did over here, and you could have an additional directory, which is in between images and your data and your images, and you can call this whatever way you want. This is a very good strategy in case you want to have, for example, a train directory containing all the training images, and then another directory which could be called validation, for example, and this is where you are going to have many images in order to validate your process, your training process, your algorithm, and you could do the same with an additional directory which could be called test, for example. Or you can just use these directories in order to label the data, right? To create different versions of your data, which is another thing which is very commonly done. So you could create many directories for many different purposes, and that will be perfectly fine, but you could also just paste all the images here, and that's also perfectly fine. And you can see that for the labels directory, I did exactly the same. We have a directory which is called train, and within this directory is that we have all these different files, and for each one of these files, let me show you like this, it's going to be much better. For each one of these files, for each one of these txt files, we will have an image in the images directory, which is called exactly the same file name, but a different extension, right? So in this case, this one is called .txt and this one is called .jpg, but you can see that it's exactly the same file name. For example, the first image is called OA2 EA8F and so on, and that's exactly the same name as for the first image in the images directory, which is called OA2EA8 and so on. So basically, for absolutely every image in your images directory, you need to have an annotations file and a file in the labels directory, which is called exactly the same, but with a different extension. If your images are .jpg, your annotations files are .txt. So that's another thing which also defines the structure you need for your data, and that's pretty much all. So remember, you need to have two directories. One of them is called images, the other one is called labels. Within the images directory is where you're going to have all your images, and within your labels directory is where you will have all your annotations or your labels. And for absolutely every single image in your images directory, you will need to have a file in the labels directory which is called exactly the same but with a different extension. If your images are .jpg, your annotations file should be .txt, and the labels should be expressed in the YOLO format, which is as many rows as objects in that image, and every single one of these rows should have the same structure. You are going to have 5 terms. The first one of them is the class ID. In my case, I only have one class ID. I'm only detecting alpacas, so in my case this number will always be 0, but if you're detecting more than one class, then you will have different numbers. Then you have the position, the X and Y position of the center of the bounding box, and then you will have the width, and then you will have the height, and everything will be expressed in relative coordinates. So basically this is a structure you need for your data, and this is what this step is about. So that's pretty much all about converting the data or about formatting the data. And now let's move on to the training. Now is where we are going to take all this data and we are going to train our object detector using YOLO V8. So now that we have taken the data into the format we need in order to train YOLO V8, now comes the time for the training. Now it comes the time where we are going to take this custom dataset and we are going to train an object detector using YOLO V8. So this is YOLO V8 official repository, and one of the things I like the most about YOLO V8 is that in order to train an object detector, we can do it either with Python, with only a few Python instructions, or we can also use a command line utility. Let me see if I find it over here. We can also execute a command like this in our terminal, something that looks like this, and that's pretty much all we need to do in order to train this object detector. That's something I really liked. That's something I'm definitely going to use in our projects from now on, because I think it's a very convenient and a very easy way to train an object detector or a machine learning model. So this is the first thing we should notice about YOLO V8. There are two different ways in which we can train an object detector, we can either do it in Python as we usually do, or we can run a command in our terminal. I'm going to show you both ways, so you're familiar with both ways. And also I mentioned that I am going to show you the entire process on a local environment in a PyCharm project, and I'm also going to show you this process in a Google Colab. So I know there are people who prefer to work in a local environment. I am one of those people, and I know that there are other people who prefer to work on a Google Colab. So depending on which in which group are you, I am going to show you both ways to do it, so you can just choose the one you like the most. So let's start with it, and now let's go to PyCharm. This is a PyCharm project I created for this training, and this is the file we are going to edit in order to train this object detector. So the first thing I'm going to do is to just copy a few lines. I'm just going to copy everything, and I'm going to remove everything we don't need. Copy and paste. So we want to build a new model from scratch. So we are going to keep this sentence, and then we are going to train a model. So we are just going to remove everything but the first sentence. And that's all. Right? These are the two lines we need in order to train an object detector using YOLO V8. Now we are going to do some adjustments. Obviously the first thing we need to do is to import Ultralytics, which is a library we need to use in order to import YOLO, in order to train a YOLO V8 model. And this is a Python library we need to install as we usually do. We go to our terminal and we do something like pip install and the library name. In my case, nothing is going to happen because I have already installed this library. But please remember to install it, and also please mind that when you are installing this library has many dependencies, so you are going to install many different Python packages. So it's going to take a lot of space, so definitely please be ready for that, because you need a lot of available space in order to install this library, and it's also going to take some time because you are installing many different packages. But anyway, let's continue. Please remember to install this library, and these are the two sentences we need in order to run this training from a Python script. So this sentence, we're just going to leave it as it is. This is where we are loading the specific YOLO V8 architecture, the specific YOLO V8 model we are going to use. You can see that we can choose from any of all of these different models. These are different versions, or these are different sizes for YOLO V8. You can see we have nano, small, medium, large, or extra large. We are using the nano version, which is the smallest one, or is the lightest one. And this one we are going to use, the YOLO V8 Nano, the YOLO V8N. Then about the training, about this other sentence, we need to edit this file, right? We need a YAML file which is going to contain all the configuration for our training. So I have created this file and I have named this file config.yaml. I'm not sure if this is the most appropriate name, but anyway, this is the name I have chosen for this file. So what I'm going to do is just edit this parameter, and I'm going to input config.yaml. This is where the config YAML is located. This is where the main.py is located. They're in the same directory, so if I do this, it's going to work just fine. And then let me show you the structure for this config.yaml. You can see that this is a very simple configuration file. We only have a few keys, which are path, train, val, and then names, right? Let's start with the names. Let's start with this. This is where you are going to set all your different classes, right? You are training an object detector, you are detecting many different categories, many different classes, and this is where you are going to input, this is where you're going to type all of those different classes. In my case, I'm just detecting alpacas. That's the only class I am detecting. So I only have one class, is the number 0, and it's called alpaca. But if you're detecting additional objects, please remember to include all the list of all the objects you are detecting. Then about these three parameters, these three arguments, the path is the absolute path to your directory containing images and annotations. And please remember to include the absolute path. I ran some issues when I was trying to specify a relative path relative from this directory, from my current directory where this project is created, to the directory where my data is located. When I was using a relative path, I had some issues, and then I noticed that there were other people having issues as well. I noticed that in the GitHub repository from YOLO V8, I noticed this in the issues section. There were other people having issues when they were specifying a relative path. So the way I fix it, and it's a very good way to fix it, it's a very easy way to fix it, is just specifying an absolute path. Remember, this should be an absolute path. So this is the path to this directory, to the directory containing the images and the labels directories. So this is the path you need to specify here, and then you have to specify the relative path from this location to where your images are located, like the specific images are located, right? In my case, they are in images./train relative to this path. If I show you this location, which is my root directory, then if I go to images train, this is where my images are located, right? So that's exactly what I need to specify. And then you can see that this is the train data, this is the data the algorithm is going to use as training data. And then we have another keyword, which is val, right? The validation data set, in this case, we are going to specify the same data as we use for training. And the reason I'm doing this is because we want to keep things simple in this tutorial. I'm just going to show you the entire process of how to train an object detector using YOLO V8 on a custom dataset. I want to keep things simple, so I'm just going to use the same data. So that's pretty much all for this configuration file. Now going back to main, that's pretty much all we need in order to train an object detector using YOLO V8 from Python. That's how simple it is. So now I'm going to execute this file. I'm going to change the number of epochs. I'm going to do this for only one epoch, because the only thing I'm going to show you for now is how this runs. I'm going to show you the entire process. And once we notice how everything is working, once we notice everything is up and running, everything is working fine, we can just continue. But let's just do this process. Let's just do this training for only one epoch so we can continue. You can see that now it's loading the data. It has already loaded the data. You can make use of all the different information, of all these different debugging information we can see here. You can see now we were loading 452 images, and we were able to load all the images, right? 452 from 452. And if I scroll down, you can see that we have additional information, additional values, which are related to the training process. This is how the training process is going, right? We are training this object detector, and this is additional information which we are given through this process. So for now, the only thing we have to do is only waiting. We have to wait until this process is completed. So I am going to stop this video now, and I'm going to fast forward this video until the end of this training, and let's see what happens. Okay, so the training is now completed, and you can see that we have an output which says results saved to runs detect train 39. So if I go to that directory, runs detect and train 39, you can see that we have many different files, and these are files which are related to how the training process was done, right? For example, if I show you these images, these are a few batches of images which were used in order to train this algorithm. You can see the name is train batch 0 and train batch 1, and I think we have a train batch 2. So we have a lot of different images of a lot of different alpacas of different images we use for training, and they were all put together, they were all concatenated into these huge images, so we can see exactly the images which were used for training and the annotation on top of them, right? The bounding boxes on top of them. And we also have similar images, but for the validation dataset, right? Remember, in this case, we are using the same data as validation as we use for training, so it's exactly the same data, it's not different data. But these were the labels in the validation dataset, which is the training dataset, and these were the prediction on these same images, right? You can see that we are not detecting anything. We don't have absolutely any prediction. We don't have absolutely any bounding box. This is because we are doing a very shallow training. We are doing a very dummy training. We are training this algorithm only for one epoch. This was only an example to show you the output, how it looks like, to show you the entire process, but this is not a real training. But nevertheless, these are some files I'm going to show you better when we are in the next step. For now, let me show you how the training is done from the command line, from the terminal, using the command I show you over here, using a command like this. And also let me show you how this training is done on a Google Colab. So going to the terminal, if we type something like this, YOLO detect train data, I have to specify the configuration file, which is config.yaml, and then model.yolo v8n.yaml, and then the number of epochs. This it's exactly the same as we did here, exactly the same. It's going to produce exactly the same output. I'm just going to change the number of epochs for 1, so we make it exactly the same. And let's see what happens. You can see that we have exactly the same output. We have loaded all the images, and now we are starting a new training process. And after this training process, we are going to have a new run, which we have already created a new directory, which is train40. And this is where we are going to save all the information related to this training process. So I'm not going to do it because it's going to be exactly the same as the one we did before. But this is exactly how you should use the command line, or how you can use this utility in order to do this training from the terminal. You can see how simple it is. It's amazing how simple it is. It's just amazing. And now let me show you how everything is done from a Google Colab. So now let's go back to the browser so I can show you this notebook I created in order to train YOLO v8 from a Google Colab. If you're not familiar with Google Colab, the way you can create a new notebook is going to go Google Drive. You can click New, More, and you select the option Google Collaboratory. This is going to create a new Google Colab notebook, and you can just use that notebook to train this object detector. Now let me show you this notebook, and you can see that it contains only 1, 2, 3, 4, 5 cells. This is how simple this will be. The first thing you need to do is to upload the data you are going to use in order to train this detector. It's going to be exactly the same data as we used before. So these are exactly the same directories, the images directory and the labels directory we used before. And then the first thing we need to do is to execute this cell, which mounts Google Drive into this instance of Google Colab. So the only thing I'm doing is just I just pressed enter into this cell, and this may take some time, but it's basically the only thing it does is to connect to Google Drive, so we can just access the data we have in Google Drive. So I'm going to select my account and then allow, and that's pretty much all. Then it all comes to where you have the data in your Google Drive, right? In the specific directory where you have uploaded the data. In my case, my data is located in this path, right? This is my home in Google Drive. And then this is the relative path to the location of where I have the data and where I have all the files related to this project. So remember to specify this root directory as the directory where you have uploaded your data, and that's pretty much all. And then I'm just going to execute this cell. So I save this variable. I'm going to execute this other cell, which is pip install ultralytics, the same command I run from the terminal in my local environment. Now I'm going to run it in Google Colab. Remember, you have to start this command by the exclamation point, which means you are running a command in the terminal where this process is being executed or where this notebook is being launched. So remember to include the exclamation point. Everything seems to be okay, everything seems to be ready, and now we can continue to the next cell, which is this one. You can see that we have done exactly the same structure. We have input exactly the same lines as in our local environment. If I show you this again, you can see we have import ultralytics, then we have defined this YOLO object, and then we have called model.train, and this is exactly the same as we are doing here. Obviously, we are going to need another YAML file. We are going to need a YAML file in our Google Drive, and this is the file I have specified, which has it's like exactly the same configuration as in the YAML file I show you in my local environment. It's exactly the same idea. So this is exactly what you should do. Now you should specify an absolute path to your Google Drive directory. That's the only difference. So that's the only difference. And I see I have a very small mistake because I see I have data here. And here I have just uploaded images and labels in the directory, but they are not within another directory, which is called data. So let me do something. I'm going to create a new directory, which is called data, images, labels. I'm just going to put everything here. Right, so everything is consistent. So now everything is okay. Images, then train, and then the images are within this directory. So everything is okay. Now let's go back to the Google Colab. Every time you make an edit or every time you do something in Google Drive, it's always a good idea to restart your runtime. So that's what I'm going to do. I'm going to execute the commands again. I don't really need to pip install this library again because it's already installed into this environment. And then I'm going to execute this file. I think I have to do an additional edit, which is this file. Now it's called googlecolab.config, and that's pretty much all. I'm just going to run it for one epoch, so everything is exactly the same as we did in our local environment. And now let's see what happens. So you can see that we are doing exactly the same process. Everything looks pretty much the same as it did before. We are loading the data, we are just loading the models, everything is going fine. And this is going to be pretty much the same process as before. You can see that now we are, it takes some additional time to load the data because now you are running this environment, you are running this notebook in a given environment, and you're taking the data from your Google Drive. So it takes some time, it's a slower process, but it's definitely the same idea. So the only thing we need to do now is just to wait until all this process to be completed, and that's pretty much all. I think it doesn't really make any sense to wait because it's going to be exactly the same process as we did from our local environment. At the end of this execution, we are going to have all the results in a given directory, which is the directory of the notepad which is running this process. So at the end of this process, please remember to execute this command, which is going to take all the files you have defined in this runs directory, which contains all the runs you have made, all the results you have produced, and it's going to take all this directory into the directory you have chosen for your files and your data and your Google Colab and so on. Please remember to do this because otherwise you would not be able to access this data. And this is the data which contains all the results and everything you have just trained. So this is how you can train YOLO V8, an object detector using YOLO V8 in a Google Colab, and you can see that the process is very straightforward and it's pretty much exactly the same process, exactly the same idea as we did in our local environment. And that's it. So that's how easy it is to train an object detector using YOLO V8 once you have done everything we did with the data, right? Once you have collected the data, you have annotated the data, you have taken everything into the format YOLO V8 needs in order to train an object detector. Once everything is completed, then running this process, running this training is super straightforward. So that's going to be all about this training process, and now let's continue with the testing. Now let's see how these models we have trained, how they performed, right? Let's move to the next step. And this is the last step in this process. This is where we are going to take the model we produced in the training step and we're going to test how it performs. This is the last step in this process. This is how we are going to complete this training of an object detector using YOLO V8. So once we have trained a model, we go to this directory. Remember to the directory I showed you before regarding the directory where all the information was saved, where all the information regarding this training process was saved. And obviously I'm not going to show you the training we just did because it was like a very shallow training, like a very dummy training, but instead I'm going to show you the results from another training I did when I was preparing this video, where I conducted exactly the same process, but the training process was done for 100 epochs. So it was like a more deeper training, right? So let me show you all the files we have produced so you know what are all the different tools you have in order to test the performance of the model you have trained. So basically you have a confusion matrix which is going to give you a lot of information regarding how the different classes are predicted or how all the different classes are confused, right? If you are familiar with how a confusion matrix looks like or it should look like, then you will know how to read this information. Basically, this is going to give you information regarding how all the different classes were confused. In my case, I only have one class, which is alpaca, but you can see that this generates another category, which is like a default category, which is background, and we have some information here. It doesn't really say much. It says how these classes are confused, but given that this is an object detector, I think the most valuable information is in other metrics, in other outputs. So we are not really going to mind this confusion matrix. Then you have some plots, some curves. For example, this is the F1 confidence curve. We are not going to mind this plot either. Remember, we are just starting to train an object detector using YOLO V8. The idea for this tutorial is to make it like a very introductory training, a very introductory process. So we are not going to mind in all these different plots we have over here because it involves a lot of knowledge and a lot of expertise to extract all the information from these plots. And it's not really the idea for this tutorial. Let's do things differently. Let's focus on this plot, which is also available in the results which were saved into this directory. And you can see that we have many different plots. You can definitely go crazy analyzing all the information you have here because you have 1, 2, 3, 4, 5, 10 different plots. You could knock yourself out analyzing and just extracting all the information from all these different plots. But again, the idea is to make it a very introductory video and a very introductory tutorial. So long story short, I'm just going to give you one tip of something, the one thing you should focus on these plots for now. If you're going to take something from this video, from this how to test the performance of a model you have just trained using YOLO V8 to train an object detector, is this. Make sure your loss is going down, right? You have many plots. Some of them are related to the loss function, which are this one, and this one. This is for the training set, and these are related for the validation set. Make sure all of your losses are going down, right? This is like a very, I would say, a very simple way to analyze these functions or to analyze these plots. But that's, I will say that that's more powerful than it will appear. Make sure all your losses are going down, because given the loss function, we could have many different situations. We could have a loss function which is going down, which I will say it's a very good situation. We could have a loss function which started to go down and then just it looks something like a flat line. And if we are in something that looks like a flat line, it means that our training process has stuck. So it could be a good thing because maybe the algorithm, the machine learning model already learned everything it had to learn about this data. So maybe a flat line is not really a bad thing. Maybe, I don't know, you will have to analyze other stuff. Or if you look at your loss function, you could also have a situation where your loss function is going up, right? That's the other situation. And if you, my friend, have a loss function which is going up, then you have a huge problem. Then something is obviously not right with your training. And that's why I'm saying that analyzing your loss function, what happens with your loss, is going to give you a lot of information. Ideally, it should go down. If it's going down, then everything is going well, most likely. If it's something like a flat line, well, it could be a good thing or a bad thing. I don't know. We could be in different situations. But if it's going up, you have done something super, super wrong. I don't know what's going on in your code. I don't know what's going on in your training process, but something is obviously wrong, right? So that's like a very simple and a very naive way to analyze all this information. But trust me, that's going to give you a lot of information in order to start working on this, testing the performance of this model. But I will say that looking at the plots and analyzing all this information and so on, I will say that's more about research. But that's what people who do research like to do. And I'm more like a freelancer. I don't really do like research. So I'm going to show you another way to analyze this performance or this the model we have just trained, which from my perspective, it's a more it makes more sense to analyze it like this. And it involves to see how it performs with real data, right? How it performs with data you have used in order to make your inferences and to see what happened. So the first step in this more practical, more visual evaluation of this model, of how this model performs, is looking at these images. And remember that before, when we looked at these images, we had this one, which was regarding the labels in the validation set. And then this other one, which were the predictions, were completely empty. Now you can see that the predictions we have produced, they are not completely empty, and we are detecting the position of our alpacas super accurately. We have some mistakes actually. For example, here we are detecting a person as an alpaca. Here we are detecting also a person as an alpaca, and we have some misdetections. For example, this should be an alpaca and it's not being detected. So we have some misdetections, but you can see that the results are pretty much okay, right? Everything looks pretty much okay. The same about here. If we go here, we are detecting pretty much everything. We have a misdetection here. We have an error over here because we are detecting an alpaca where there's actually nothing. So things are not perfect, but everything seems to be pretty much okay. That's the first way in which we are going to analyze the performance of this model, which is a lot, because it's like a very visual way to see how it performs. We are not looking at plots. We are not looking at metrics, right? We are looking at real examples and to see how this model performs on real data. Maybe I am biased to analyze things like this because I'm a freelancer, and the way it usually works when you are a freelancer is that if you are building this model to deliver this project for a client and you tell your client, oh yeah, the model was perfect, take a look at all these plots, take a look at all these metrics, everything was just amazing, and then your client tests the model and it doesn't work, the client will not care about all the pretty plots and so on, right? So that's why I don't really mind a lot about these plots. Maybe I am biased because I am a freelancer and that's how freelancing works. But I prefer to do like a more visual evaluation. So that's the first step we will do, and we can notice already we are having a better performance. We are having an okay performance. But this data we are currently looking at right now, remember the validation data, it was pretty much the same data we use as training, so this doesn't really say much. I'm going to show you how it performs on data which the algorithm have never seen, with completely and absolutely unseen data. And this is a very good practice if you want to test the performance of a model. So I have prepared a few videos. So let me show you these videos. They are basically, remember this is completely unseen data. And this is the first video. You can see that this is an alpaca, which is just being an alpaca, which is just walking around. It's doing its alpaca stuff. It's having an alpaca everyday life. It's just being an alpaca, right? It's walking around from one place to the other, doing nothing. No, it's doing its alpaca stuff, which is a lot. This is one of the videos I have prepared. This is another video, which is also an alpaca doing alpaca related stuff. So this is another video we are going to see. Remember, this is completely unseen data. And I also have another video over here. So I'm going to show you how this model performs on these 3 videos. I have made a script in Python which loads these videos and just calls the predict method from YOLO V8. From YOLO V8, we are loading the model we have trained and we are applying all the predictions to this model, and we are seeing how it performs on these videos. So this is the first video I show you, and these are the detections we are getting. You can see we are getting an absolutely perfect detection. Remember, this is completely unseen data, and we are getting, I'm not going to say a 100% perfect detection because we are not, but I would say it's pretty good. I would say it's pretty good in order to start working on this training process. Yeah, I would say it's pretty good. So this is one of the examples. Then let me show you another example, which is this one, and this is the other video I show you, and you can see that we are also detecting exactly the position of the alpaca. In some cases the text is going outside of the frame because we don't really have space, but everything seems to be okay in this video too. So we are detecting exactly the position of this alpaca. The bounding box in some cases is not really fit to the alpaca face, but yeah, but everything seems to be working fine. And then the other video I show you, you can see in this case the detection is a little broken. We have many misdetections, but now everything is much better. And yeah, in this case it's working better too, it's working well. I will say in these 3 examples, this one it's the one that's performing better, and then the other one I really like how it performed too, in this case where the alpaca was like starting its alpaca journey. And yeah, we had like a very good detection and a very stable detection. Then it like breaks a little, but nevertheless I would say it's okay. It's also detecting this alpaca over here, so I would say it's working pretty much okay. So this is pretty much how we are going to do the testing in this phase. Remember that if you want to test the performance of the model you have just trained using YOLO V8, you will have a lot of information in this directory, which is created when you are training the model. At the end of your training process, you will have all of these files, and you will have a lot of information to knock yourself out to go crazy analyzing all these different plots and so on. Or you can just keep it simple and just take a look at what happened with the training loss and the loss and the validation loss and so on, all the loss functions. Make sure they are going down. That's the very least thing you need to make sure of. And then you can just see how it performs with a few images or with a few videos. Take a look how it performs with unseen data, and you can make decisions from there. Maybe you can just use the model as it is, or you can just decide to train it again. In this case, if I analyze all this information, I see the loss functions are going down, and not only they are going down, but I notice that there's a lot of space to improve this training, to improve the performance, because we haven't reached that moment where everything just appears to be stuck, right? Like that flat line. We are very far away from there. So that's something I will do. I will do an even deeper training so we can just continue learning about this process. Also, I will change the validation data for something that's completely different from the training data, so we have more information. And that's pretty much what I will do in order to iterate and in order to make a better model and a more powerful model. Now let's get started with this tutorial. This is Detectron2 official repository, and this is exactly the framework we are going to use today. I have used Detectron2 many times in my project as a computer vision engineer. I think it's an amazing framework, an amazing algorithm, and in this video I'm going to show you how to train an object detector using Detectron2. Now the first thing I'm going to do is to show you the data we are going to use today. Now, we're going to use the same alpaca dataset we already used in one of my previous tutorials. If you watched my previous video on how to train an object detector using YOLO V8, then most likely you are already familiar with this dataset. This is exactly the data we are going to use in this tutorial too, and this is how the images look like. Now, it's very important that in my case, I already have the annotations of this data. You can see all of these TXT files. This is my annotations. These are my annotations for all my data, for all my images. But if you're watching this tutorial, then most likely you want to know how to train Detectron2 on your own custom data. And most likely you want to know how to do all the annotation, right? You want to build this dataset from scratch. You want to annotate all of your images. And the annotation of an object detector dataset, it's something I have already covered in one of my previous videos. In my previous video where I show you how to train an object detector using YOLO V8. I think it doesn't really make a lot of sense to cover the entire process again in this tutorial, so if you are curious to know how to annotate your custom data, then go ahead and watch that other video. I'm going to post a link somewhere in this video. And now let's go to PyCharm, to a PyCharm project I created for this tutorial, and these are the requirements for this project. As always, please remember to install these requirements before starting with this tutorial, otherwise nothing is going to work. So please remember to install these packages, and now let me show you these three files. They are called train.py, util.py and loss.py. Let's start with train.py. This is the file we are going to execute in order to do all of our training process, and you can see it all starts with a very long doc string explaining how you need to format your data. This is very important. In the util.py and loss.py we have many different functions, and we also have a class definition. We have many different code. We have a lot of code which already handles the entire training process, already handles the parsing the data, already handles everything. So the only thing you need to do in order to make this training process to work as expected is to put the data into this format. To put your file system into this format too, you need to put everything as it's specified in this doc string. So let me show you. You can see that the annotations should be provided in YOLO format. This is this format, class XC, YC, which is the X and Y position of the center of the bounding box of the annotation, and then the width and the height of the bounding box. Now let me show you one of my annotation files. Let me show you how it looks like. You can see, for example, in this case, we have 5 numbers. The first one is a 0, and then we have 4 float numbers. So this is exactly the annotation, the bounding box in YOLO format. The first number, the 0, is the class ID, which in my case is always going to be 0 because I only have one class in this dataset. And then these two numbers are the X and the Y positions of the center of the bounding box. These two numbers are the center of the bounding box, and then this number is the width, and this number is the height of our bounding box, right? So please remember to format all of your annotations into the YOLO format, which looks exactly like this. Class ID, X and Y position of the center of the bounding box, and then the width, and then the height. And then your file system needs to be structured exactly like this. Let me show you in my computer, in my file system. If I go to data, this is my root directory where my data is located. You can see I have 2 folders. One of them is called train, the other one is called val. Within train, I have 2 other folders. One of them is called images, and the other one is called ans. Within images is where I have all my images, all my training images, and within ans is where I have all my annotations for my training images. And then if I go to val, you can see exactly the same structure. I have 2 folders. One of them is images, the other one is ans. Within images, I have all my images, and within ans, I have all my annotations for the validation data. Now, this is exactly what's described here, right? You can see that we have a data directory, and within data directory, we have 2 folders, train and val. Within train, we have 2 additional folders, images and ans. And the same about val, we have 2 directories, trains and ans. And then this is exactly what I show you in my local computer. And then for absolutely every single image in this directory, we have an annotation files in this other directory with exactly the same name, but a different extension. This is very important, and please remember to structure your data, your file system exactly like this. Otherwise, nothing is going to work, because all the functions which are in this file, which handle all the parsing and reading the data and getting the annotations and so on, all of these functions are expecting the data exactly like this. So please remember to structure everything as it's described in this docstring, otherwise you are going to have issues in this training process. Now let's continue. If I scroll down, you can see I have this arg parser, and these are all the arguments we can specify, we can define for this training process. You can see that we have the data directory, obviously this is very, very important. Then we also need to define what are all the names of our classes. If I go to my file system, you can see that in my case I have this file which is class.names, and in my case it only contains one class name, which is alpaca. But if you are doing something like a multi-class object detector, then most likely you are going to have other classes as well. Now let's go back to PyCharm. You can see that another argument is the output directory. This is where all the models and all the results, everything is going to be saved. And then we have different hyperparameters. For example, the learning rate. This is going to be the learning rate of our training process. Then the batch size, the number of iterations of our training process. Then the device, if we want to do this training in a CPU or in a GPU, this is very, very important. Then this argument is the checkpoint period, which means how often we are going to save the weights of the model we are training, right? We are going to be training by this number of iterations, and a given number of iterations, every 500 iterations, we are going to be saving the weights of this model. And this is something we are going to see later on this tutorial when we are doing the validation of the model we trained. Now, another hyperparameter which is very, very super amazingly important is model. This is where we are going to specify the baseline we are going to use in order to do this training process. In my case, this is the baseline I have set. You can see it's Coco detection RetinaNet R101. And now let me show you something that's very, very important, which is where this model comes from. Let me show you in my browser. This is Detectron2 model SU and baselines. This is very, very, very important. When you are working with Detectron2, you have many models to choose from. So this model SU is basically the collection, a very, very large collection of all the baselines, of all the pre-trained models you can choose from when working with Detectron2. If I scroll down, you can see that we have many different sections. For example, here we have a section which is Coco object detection baselines. Then we have another one for instance segmentation. We have another one for key point detection. Then panoptic segmentation, and so on, right? We have many different sections for all the different type of algorithms, right? You can see that we have many models, many architectures, many baselines we can choose from. And basically the idea is that when we are training our own model, when we are training our custom model, we can just take whatever pre-trained model we want, we can take whatever baseline we want, and we can just train our own model on top, right? This is very important because you can see that we have many different metrics, or we have all the different performances of all of these different models. We also have the inference type, the inference time of all these different models. So this is amazing because we can just choose a model we like the most for the specific project we are working in. And in my case, this is the model I have selected. I have selected the RetinaNet R101. So this is the model we are going to be using in this tutorial. But in your case, please go ahead and choose whatever model you want, because it's basically the same. I mean, the entire process I'm going to show you in this tutorial is going to work exactly the same for whatever other model you want to choose from here. So this is the model SU, this is Detectron2, the model SU, and please take a look at this SU, take a look at all the models which are available, and this is just amazing. You can see that this is like a very large collection, and it's just amazing. So let's go back to PyCharm, and you can see that this is where you are going to specify the architecture, the model you are going to use in your training process. Now let's continue. You can see that after I just parse through all of these different arguments, the only thing I'm doing is calling util.train. I am calling the train function, which is defined in my util.py file. And I am just calling this function from a very, very high level, right? I'm just calling this function, I'm putting all these arguments as input, and that's it. And this function is going to take care of the entire training process. If you have watched my previous tutorials on YOLO V8, the image classifier, the object detector, the instance segmentation model, the key point detector, absolutely all of my models, you will remember that the training process is super simple, super straightforward. The only thing we need to do with YOLO V8 is to code a couple of lines and that's it. So for this video, for Detectron2, I wanted to give you something that's like the same level of complexity, the same level of abstraction, right? I wanted to give you something super high level, which you can just go ahead and use without really caring about all the different details and about everything that's working under the hood, right? So that's why I made this train.py file like this, right? You can just set up all of your arguments and then you can just call train. And you can just forget about all the complexity about using Detectron2. That's something I wanted to do for you because that's going to make things much simpler for you to just train your model on your custom data and that's it. And I don't know about you, but in my case, Detectron2, YOLO V8, or whatever other machine learning framework, algorithms, whatever you can think of, for me, they are only tools I use to solve my problems. Right? So being able to train an object detector using Detectron2 by just calling a function like this from a very high level for me is amazing. I don't know about you, but if you're anything like me, then you're just going to be super happy with this function. And if that's the case, then just jump to the next chapter where I'm going to show you how to continue this training process and how to do this training from a Google Colab. But if you do care about the details, if you do care about how everything works, like under the hood, if you want to know exactly how these functions work and exactly how the data is parsed and everything, if you want to know more details, then just continue watching and I'm going to give you more details. And now let's move to util.py. You can see that we have 4 different functions and these functions are the functions that take care of the entire training process. So let me start with train. This is the function we are calling over here in order to start with the training process. So this is a very good place to start with this util.py file. You can see that we have many different parameters, many different arguments into this function, and for each one of these parameters, for each one of these arguments, we have a very short description of what they mean, of what this parameter is. So this is very important, and please remember to take a look at this documentation, at this docstring when you are reviewing this file, when you are reviewing this function, because this is going to help you a lot to further understand what each one of these parameters and arguments mean. Now let's continue. We can see that the first line, we are calling another function. We're calling another function in this util.py file, which is register datasets. By the way Detectron2 works, we always need to register the datasets before starting with the training process. Now let me show you this function, and this is another function in the util.py file. You can see that we are taking 2 parameters as input, which is the root directory and the class list file, and basically the only thing we're doing in this function is calling this method. We're calling dataset catalog.register and we are just doing something else, right? We are just taking these 2 arguments as input into this function. But basically just remember that in this function we are registering the data, all of our annotations into Detectron2. And this is a very important step when we are working with Detectron2. You can see that we are registering the training set under the keyword train, and we are registering the validation set under the keyword val. This is very important because we are going to make a reference to these 2 words, to train and val, later on, so please remember. And then the second argument is this lambda function we have over here, and you can see that basically we are calling another function in this util.py file, which is called getDicts. So this is basically the function we are calling over here, and we are putting these 2 arguments, which is basically the location of the images and the location of the annotations for the training set and for the validation set. We are iterating in the training set and in the validation set, and for each one of these iterations we are registering each one of these sets. Right? Now let me show you this other function, getDicts. And you can see that basically the documentation we have in this function is very proper. It's a very good documentation, and it says read the annotations for the dataset in YOLO format and create a list of dictionaries containing information for each image. The arguments are a directory containing images and another directory containing annotations, and the return is a list of dictionaries with all this information. The file name for every single image, and a unique identifier for every image, then the height and the width of the image, and then the annotations, the bounding box, and also the category ID, the class ID, right? And if I show you the code, it's very straightforward. The only thing we're doing is iterating in absolutely all the files in the annotations directory, and for each one of these files we are opening the image for this annotation, the image that belongs to this annotation, and then we are just taking the height and the width for this image, and we are just creating this dictionary with all the information, which is the image file name, the ID, the height and the width of this image, and we are just saving everything into a dictionary. And then the only thing we're doing is we are parsing through all the annotations, and we are just getting all the bounding boxes, and we are just getting also the class ID, right? So basically we are parsing through all of our data, and we are getting all the information of our images and all the information of our annotations. And something that's very important is that if you remember, our annotations are specified in the YOLO format, which means it's the class ID, and then it's the X and Y position of the center of the bounding box, and then it's the width, and then it's the height. And we are converting the annotation into another format, which is the XYWH in absolute coordinates. This is very important because this may be confusing, but just remember that we are taking the annotation which is in the YOLO format and we are converting into this other format. XY means that it's the upper left corner, and then it's the width, and then it's the height of the bounding box, right? So that's basically what we are doing here. We are converting the annotation from this format into another format, and then it's just getting the class ID, and that's basically all. And at the end of this function we are returning this list, right? This is a list of dictionaries with all this information, right? So just go through this function, and it's going to be super straightforward, and you have this super comprehensive docstring telling you exactly how everything works, and all the input parameters and all the output and so on. So this is all for this function, for the getDicts. And now let's continue by reading register datasets. So after we register the dataset, the training dataset and also the validation dataset, then we need to tell Detectron2 exactly what are the class names, right? Because so far we are parsing through the data, we are parsing through the annotations, but we are only parsing through the class IDs, right? The annotations, they only contain the class ID, but they don't really have the class name. So it's very important for Detectron2, it's very important we tell Detectron2 what are the class names, and that's why we are calling this function after we register the datasets. So that's pretty much all for this function for register datasets, and now let's continue. So after we register the datasets, we can continue with the next line, which is getConfig. This is where we are going to create the entire configuration file we are going to use in this training process. And the first line is getConfig, and this is basically a Detectron2 built-in function, and basically we are getting something like a default configuration file with many default hyperparameters. That's basically what we are getting here, a very long, very comprehensive default configuration file. And then the next line, we are updating this file with many other values which are specific to the specific model we are using here, right? In my case, it's RetinaNet R101, and basically after we are getting this default configuration file, we are just updating this file with many other values which are specific of this model, right? That's very important. And then the only thing we're doing is just setting other values. We are just manually updating other values in this config file, right? You can see that for each one of the other lines, it's config dot a given key, and it's the value for that key, right? In this case, we are updating the value of the training set, the validation set, the test set, and so on, right? It's very self-explanatory, each one of these configuration values, right? For example, here we are telling Detectron2 to use CPU. Here we are setting the weights of this model, which is basically the pre-trained weights of this model we have over here. And then we are also setting the batch size, the checkpoint period, which is how often we're going to be saving the checkpoints, the learning rate, and so on. And I would say this is the most important part of this function by far, right? Because this is where we are telling Detectron2 where is the training data and where is the validation data, right? Because we have registered the data sets, and if you remember, we called one of the data sets train, and we called the other dataset val. So this is where we are telling Detectron that the training data is the dataset we register under this keyword train, and the validation data is the dataset we register under this keyword val. This is very, very, very important, and this, I would say, it's the most important part of this function. And that's basically all for this get config. Now let's continue. And you can see that then the only thing we're doing is we are creating the output directory. Then we are creating this object, which is the trainer with the one that's going to take care of the training process. Then this line, and actually these 3 lines we have over here, this is also very important because when we are training a model using Detectron2, during the training process, we will have a lot of information regarding the loss function in the training set. But we will not have any information regarding the loss function in the validation set. That's the way Detectron2 works by default. So if we want to add this information, if we want to add the loss function in the validation set, if we want to access this information, this is exactly what we need to do. And this is why I created this class we have over here, which is validation loss. This is the class which is defined in loss.py. So long story short, these 3 lines we have over here, it's related to creating this custom output, creating this custom debugging information regarding the training process, so we have more information regarding how the training process is doing, how the training process is going. And this is very important because this way we are going to have additional information, and this is going to be super useful once we are validating this model. So now let's continue. You can see that this line is resume or load, and this is pretty much if we are resuming this training or if we are training from scratch. And in my case, I'm training from scratch, so the resume equal false, and then the only thing I'm doing is calling trainer.train, and this is pretty much all it takes in order to start this training process, and that's pretty much all. So this is a much more detailed explanation of these 4 functions we have here in the util.py file, and also of the function, or actually the class definition we have here in loss.py. So this is all in order to give you more details regarding all these other functions and this class definition and so on. And now let's continue and let's go back to train.py, because now that we already have all the code we need in order to do this training, the only thing we need to do is to press play. And that's it. You can see I press play, I get some huge output. And this is, I'm just going to stop the training. I'm going to show you something. This is pretty much all the model, all the network, all the hyperparameters for this network we are using in order to train this model. In my case, remember, it's RetinaNet R101. And then the only thing we will need to do from now on is just wait until the training is completed. But in my case, I'm not going to train it locally because it's going to take a lot of time. I'm going to show you how to do this training from a Google Colab, because this is going to make the process much simpler and much faster. This is going to take care of the entire training process much faster if I will do it in my local computer. So I'm going to tell you how to do it from a Google Colab. The first thing you need to do is to obviously upload your data. And this is very important. Please remember to upload your data, otherwise obviously you will not be able to train this model from a Google Colab. And in my case, you can see that this is my data, the same data I show you in my local computer. These are my train and my val directories. And now you also need to upload these files, which are util.py, train.py, loss.py, and class names, right? So basically is these files over here, train.py, util.py, loss.py, and also the class names, which is this one. So remember to upload all these files, otherwise nothing is going to work. And now let's move to this Google Colab, to this Jupyter Notebook, and I'm going to tell you exactly how you can train this model from here. Basically, this is a very straightforward process. The only thing you need to do is to execute each one of these cells. So it's something very, very simple to do, and we are just going to be executing the code we have over here. The first step is to connect your Google Colab with Google Drive. So basically you need to execute this cell and you need to wait a couple of minutes. Click on Connect to Google Drive. I select my account. I scroll all the way down and I click Allow. And that's pretty much all. Then I need to wait a few seconds, and that's going to take care of connecting my Google Colab with Google Drive. Okay, so everything is completed. Then I'm going to continue with the next cell. I'm going to run this, install these requirements, which is running all this pip install. This is going to be very straightforward. The only thing you need to do is wait until everything is completed. Okay, that took a few minutes, but now it's completed, and you can see that I have an output over here. You must restore the runtime in order to use newly installed versions, and if I scroll up, I got a similar output over here. So basically, remember to restore the runtime if you have a similar message, and that's going to be pretty much all. So the Google Drive is now mounted, so everything is okay. We have installed the requirements. Now let's continue. Then you need to change the working directory of this notebook. So you need to execute this cell, but it's very important you update this path to the path where you have uploaded the data and all of your files, right? In my case, it's content, G drive, my drive, and then this is the location of my data. If I show you my Google Drive, you can see this is my drive, computer vision engineer, train Detectron2, object detector. And if I show you here, my drive, computer vision engineer, train Detectron2, object detector. So please remember to update this path with the location of your data in your Google Drive. Your data and also your files, right? Everything should be located in the same directory. Once you have edited this location, the only thing you need to do is to press Ctrl Enter, and then that's going to be pretty much all in order to change the working directory. And then the only thing you need to do is to execute this cell. So you can see that we are executing the train.py file, and I'm setting these arguments, which are the device. I am setting device into GPU. It's very important because that's pretty much the reason why we are using a Google Colab, a Jupyter Notebook in Google Colab. So this is very important. Then I am also setting the learning rate in this value, and I am going to train for 6,000 iterations. I will say these two values, these two arguments are not absolutely needed. You can just use the default values, but in my case, for my data, for my problem, I noticed these values were better. It was much better to use this learning rate, and also it was better to do a shorter training. Only 6,000 epochs will be just fine. So now I have to press enter. I need to execute this cell, and that's going to be pretty much all to this training process. You can see how simple this is once everything is within this train.py file, right? Once I create these functions and I put everything in this util.py, we can just execute everything from a super high level calling train.py. And please let me know what you think in the comments below, but I think it's just amazing. We can just train Detectron2 from a super high level as we are doing over here. The only thing we're doing is calling train.py, and we are passing the arguments exactly like this. From a super high level, we don't really care about the details, we don't really care about the complexity, we don't really care about nothing. It's amazing. I don't know what you think, but I think it's amazing. Please let me know in the comments below what you think. So this is pretty much all for this training. The only thing we will need to do now is we will need to wait until everything is completed, and this is going to take some time. This is going to depend on your data, on your annotations, on your problem, on your specific problem. In my case, for my data, it took something like 2 hours to do the entire training process. So we are not really going to wait until this is completed because I have already trained this model when I was preparing this tutorial. So let me just show you what the output looks like. Once you train your model, you are going to have a directory which is called output, exactly like the one I have over here. And this is where you're going to have all the results of your training process. You can see, you're going to see all of these models, all of these checkpoints, which are the weights of your process, of your training process in all these different steps, right? And this is where we are going to notice this argument over here, checkpoint period, because we have said that the checkpoints should be saved every 500 steps. And if you notice, these are all the checkpoints, these are all the weights we have saved, and if you check the numbers, you can see that these are 499, then 999, 1499, and so on. So all of these files are 500 steps apart. And yeah, so that's basically what it means to save the checkpoints every 500 epochs. At the end of your training process, or actually during your training process, you are going to be saving the checkpoints, the weights, exactly like this. So at the end of your process, you are going to have many weights files, exactly like I have over here. So these are my weights, but what I'm going to do is I'm going to take this file. This is the file with all the information of our training process in the training set and in the validation set. So this metrics.json file is the one we are going to inspect, is the one we are going to analyze to validate this model. So I'm just going to download this file. And now let's go to PyCharm because I want to show you this file, which is plotloss.py. So I have already downloaded this file and it's in my directory. Let me show you today's tutorial, Detectron2 code. And this is my metrics.json file I have just downloaded. And now if I show you this plotloss.py, basically what we are doing over here is parsing through this file, right? Parsing through all the information we have in this file. Let me open this file for you so you can see exactly how the information looks like. You can see it looks very crazy, right? We have a lot of values, we have a lot of information, and basically we need a way to parse through this information, and we need a way to visualize all this information super quickly. So that's why I created this plotloss.py, because it's going to help us a lot in order to just get all the information we want from this file and just plot everything into a very nice looking plot, so we can just do this validation much quicker. So let me show you how it looks like. I'm just going to press play. I'm going to tell you in a few minutes why I have commented these two lines. I'm going to press play, plot loss, play. And you can see that this is the training loss and the validation loss. The blue values are the training loss and the orange values are the validation loss. But obviously this is something that we cannot analyze because this is a lot of information. This doesn't really look very well, right? So we're going to do something now which is going to make everything much prettier, which is we're going to do a moving average on each one of these functions. Basically we are going to apply another function which is going to smooth these values, and it's going to make everything much smoother. I already made all the code we need, and I already made this function which is moving average, and the only thing we need to do is I'm going to delete these comments, and basically now we are going to plot the loss values, the same loss values we are getting from this metrics.json file, and then we are also plotting the moving averages, right? We are plotting the same functions but the averages. And you can see that this is how the averages look like, right? This is something that's much prettier. And in order to show you much better, I'm just going to remove these two plots, and we are only going to plot the moving averages, right? This is much prettier, this is much better. So now we have in blue the training loss. I'm going to adjust the labels. Okay, now you can see that everything looks better. We have these values over here. In blue we are plotting the training loss, and in orange we are plotting the validation loss. And we can see that both of these functions are going down, and that's a very good sign. But in the case of the training loss, it seems we have reached a plateau over here. So the training process, it goes super smoothly until it reached something like 5,000 steps. And in the case of the validation loss, it seems we also reach a plateau, but much sooner, right? So this is basically where we are going to validate this model, and this is also where we are going to decide which one of our checkpoints we are going to choose from this model, right? Because we have many weights, we have many checkpoints, and we can just use any of these files in order to produce our inferences, in order to produce our predictions. So this is where we are going to define exactly which one of these checkpoints we are going to use. And I would say I like how everything is going until this point over here, because you can see that the training loss is going down and the validation loss is kind of going down as well. And this is pretty much where everything is like a plateau, right? So if you ask me, I will keep this checkpoint over here in the 3000 epochs. So in the 3000 steps, this checkpoint over here. So this is where you're going to draw your conclusions and you're going to make decisions regarding what you're going to do next. Obviously, another conclusion could be to do the training again. It all depends on what's going on with your data. Ideally, your training loss and your validation loss should be like closer together, right? In this case, they are very far apart, and that's something I don't really like. But that's like ideally. I think that if we take this model over here in the 3000 steps, I think everything is going to be just fine. But ideally, I would like to have like these two plots more closer together, right? Because otherwise, this could mean the model is overfitting to the training data, and the model is not going to perform well in unseen data. But never mind, let's just take this model, the one we trained over here in the 3000 steps, and let's see what happens. So I'm just going to get back to PyCharm, because now it's time to make our predictions. Now it's time to take the model we trained, to take the checkpoint we chose, and let's just make some predictions with this checkpoint, with this model. So let me show you how to do that. I'm going to this file, which is predict.py, and this is the file we're going to use in order to make our predictions. And you may see that everything is already coded. So everything is ready, and I'm just going to explain absolutely every single line of this file so you understand exactly how it works and you understand exactly every single line of this file. You can see that the first few lines are a few imports. So I'm just importing a few functions which are important in order to make these predictions. These are a few imports from Detectron2, and I'm also importing CV2. Then the first line is getting a configuration file. Absolutely every single time we use Detectron2, we need a configuration file. We need an object which is going to contain all the configuration for the specific task we are going to do with Detectron2. In this case, we are just getting this default configuration file with a lot of default values, and then we are updating this file, this default configuration, with many other values which are specific to the model we use. In my case, as I used this model, as I used this pre-trained model, this baseline, I have to use exactly the same one here, and the only thing I'm doing is updating this default configuration file with many other values which are specific to this model. Then, this is very important, I am setting the model.weights to the location, the path of the checkpoint we are going to use. And if I show you my Google Drive, remember these are all the checkpoints we generated with this training process, and as I am going to use the one we generated at the 3000 steps, this is the one I have already downloaded and it's already in my file system. You can see that this is the directory, the folder of my PyCharm project, and this is the file we are going to use. model/0002999.pth. So this is exactly the file we are going to use, and this is exactly the location of this file. Then, as I am going to make these predictions in my local CPU, I am setting device to CPU. Then I am creating this object, which is this predictor, and basically this is going to be the predictor we are going to use in order to make our predictions. Then I am loading an image, very important because we definitely need an image if we are going to make predictions, and this is the image I am loading. Let me show you. This is exactly the image of an alpaca we are going to use in order to make predictions. Ideally, we should be getting the location, the bounding box of this alpaca. Let's see what happens, but this is what we should get. Ideally, we should get the location of this alpaca. And this is the location, the path to this image, right? You can see it's data, val images, data, val images, and then it's just this name. If I search, you can see this is the image we are going to use. Now let's go back here, and then the only thing we need to do is to call predictor, and we need to input the image we are going to predict, and then we are just going to get all the outputs, right, all the results. But let's just stop for a minute and let me show you exactly how output looks like. I'm just going to print outputs. I'm going to comment everything else. This is maybe the only coding I'm doing in this tutorial. So I'm just going to press play. And you can see that this is the output we got, right? So these are the predictions for this image. You can see that we have many different fields. One of them is pred boxes, and these are basically all the bounding boxes, all the objects we are detecting. This is the first one, and then these are all the other objects. We are detecting something like eight different objects in this image. And this is very important. These are all the bounding boxes, and these are the X and Y coordinates of the top left corner, and these are the XY coordinates of the bottom right corner. So these are the bounding boxes. You can see that we are also detecting the scores. We are also getting information regarding the scores, the confidence values of each one of these bounding boxes. For example, the first one is 88.6% and the last one is 5%. So you can see that these are all the different confidence values. And then we are also getting this information, which is the class we are predicting, right? In my case, I'm only using one class, which is alpaca, and it's encoded with the number 0. But this is where you will have all the different numbers of all the different class IDs of all the objects you are detecting. And please mind that in my case, although my dataset contains only one class ID, because I'm only detecting alpacas, you may notice that some of these objects were detected with a different class ID. I have a 39, 47, 56. I have used Detectron2 many times in many projects, and this is an issue I have found in different projects. So you can see, for example, in this case, I should be getting only zeros because I only have one class in my dataset, but I'm also detecting other random numbers. So please take a look at the numbers you are getting here, and please take a look that everything makes sense, and just make sure you are only detecting the numbers you should be detecting. And if you are getting some random numbers, as I'm doing right now, just don't use those predictions. Do something like an if, something like that. And if the number you're getting is not within your predictions, it's not within your classes, then just don't use those predictions. Do something like that. But also in my case, for example, now you can see that the random numbers, the random values, are some detections with a very, very low confidence. For example, this one is the fourth one. So 1, 2, 3, 4. This one, which is something like an 8% confidence. And then this one, which is a 5.8%, and this one, which is a 5.3%. So I guess it's most likely this is going to be an issue with those objects with a very, very low confidence value, but you never know. So please make sure the numbers you are getting, they make sense. Now let's continue. So I show you the output you are getting from Detectron2. Now I'm just going to uncomment everything, and I'm going to continue explaining this file. So you can see that the next line, it says threshold equals 0.5, and this is the detection threshold we are defining. So we are only going to consider valid all of those detections with a confidence value which is higher than 0.5. Now let's continue. You can see that this is basically we are parsing through the outputs. You can see that we are detecting 3 objects: the pred boxes, the scores, and the pred classes, right? So the only thing I'm doing is I'm parsing through this information and I'm just getting these objects: pred classes, scores, and bounding boxes. And then I am iterating in all the bounding boxes, and for each one of these boxes I am getting the score, the confidence score of that specific detection. I'm getting the class ID I'm detecting, the number of the class ID I'm detecting, and then if the confidence value is greater than the threshold, then I am just getting all the values, the XY position of the top left corner and the bottom right corner, and then I'm just drawing a rectangle on top of my image. I'm not really checking that I am getting only zeros. I am not doing it here, but that's a very good homework for you. I invite you to make an edit into this file, and you make something like an edit, for example here, and you say something like, if the confidence score is greater than the detection threshold and pred is within the class IDs of my class.names file, of this file over here, right? If the prediction we are getting is within my classes, is a valid number, if I'm getting a number which makes sense, then and only then draw the bounding box, right? That's a homework for you. That's a very, very good homework for you. So yeah, I'm just going to continue, and you can see that I'm drawing the bounding box, and then the only thing I'm doing is plotting this image. So let's see what happens. Now I'm going to press play, and let's see if we are detecting this alpaca properly or not. Amazing! We are detecting the alpaca super properly. Remember, this is the image we are using, and we are just detecting the only alpaca we have in this image. And yeah, we are just drawing the bounding box, and the bounding box is enclosing the alpaca super properly. So everything is working just fine. So this is going to be all for this tutorial. This is exactly how you can train your object detector on your own custom data using Detectron2, and this is going to be all for today. Hey, my name is Felipe and welcome to my channel. In this video, I'm going to show you how to use Amazon Rekognition as an object detector. Amazon Rekognition is a very interesting tool and a very powerful tool which I have used many times in my projects as a computer vision engineer. Now let me show you super quickly all the different categories, all the different objects you can detect using AWS Rekognition. And you can see that this is a very long and a very comprehensive list of objects, right? For example, you can detect dinosaurs, you can also detect diamonds, you can detect driving licenses, e-scooters, and so on. If I scroll down, you can see that these are many categories, and in total we have something like 290 different objects. So this is definitely a lot. And this is a very interesting tool because there are many cases, in many situations, in many projects in which you need to detect a very specific type of object, and in some cases it may not make a lot of sense to train an entire object detector only to detect a very specific object. In some cases it may be more convenient and it may be easier and it may be quicker, much quicker, to just use something like Amazon Rekognition out of the box, and you can just detect all of these different objects in the list, right? For example, if we were working in a project and we need to detect wheels, we can either train an object detector from scratch to detect wheels, or we can just use Amazon Rekognition out of the box, right? So this is a very interesting tool and I have used it many times in my projects, and this is exactly what we will be doing today. And in this video, I'm going to show you how to use Amazon Rekognition to detect zebras. This is a random category, a random object I have chosen from this list. So this is exactly the object we will be using in order to show you how to use Amazon Rekognition. Now, let me show you super quickly the video we are going to use as an example so we can use this tool. And you can see that this is a video in which we have many zebras. We are going to use this video in order to detect all the zebras and in order to show you how to use Amazon Rekognition. Now, what we're going to do now is going to PyCharm, and I'm going to show you the entire process of how to create a project, how to create all the files we need, how to install the requirements. I'm going to show you absolutely every single step of this process. We are going to start this project and we're going to build this project from scratch, right? So the first thing I'm going to do is I have already opened PyCharm. I'm going to File, New Project, and I'm going to just create a project, and I'm going to create this project exactly here, which is this folder I have over here, and I'm going to create it here where it says tutorial AWS Reco. This is where you are going to choose the exact directory where you want to create your project. Then I'm going to create a new environment, and this is where my environment is going to be located, and I'm going to create this environment using Python 3.8. Now I'm going to click on Create. I'm going to choose this window because I'm going to open this project over here. And you can see that this is a completely and fully and absolutely empty project. The only thing we have is the virtual environment, which is called EMB, and that is it. Now, the first thing I'm going to do is to install the requirements, is to install the Python libraries we are going to use today. So I'm going to Settings, then I'm going to Project and Python Interpreter, and I'm going to click on this button, this plus button over here, and then I'm just going to choose, I'm going to type OpenCV Python. This is one of the libraries we are going to use. I'm going to click on Install Package. And then we are also going to use Bodo3, and that's pretty much all. These are the two libraries we need in this project. And then I'm just going back to PyCharm, and now I'm going to create the first file we are going to use in this project, and I'm going to click here, New Python file, and then I'm going to call this file main.py. So the first thing I'm going to do for now is to just write the entire pipeline, the entire process we will be doing today. The first step will be to create an AWS Rekognition client. AWS Reco client, right? This is going to be the first step in this process. Then we are going to set the class, set the target class we are going to be detecting, right? I already mentioned we were going to detect zebras in this tutorial. So this is exactly where we are going to specify exactly what's the object, what's the category we are going to be detecting. Then we are going to load the video, right? The video we are going to detect today. Then we are going to read frames from the video. The next step is to convert the frame to JPG. This is a very important step. Then we are going to convert this, we're going to get a buffer from this conversion, and we're going to convert this buffer to 2 bytes, right? This is going to be the next step in this process. Then the only thing we need to do is to use Amazon Rekognition in order to detect objects, and then we are going to write all the detections to our file system, right? We are going to write everything to our disk, to our local computer. And this is exactly the process in which we are going to be working today. Now, let me show you something else. I'm going to create another file which is called credentials, because in the first step in this process, we are going to create this AWS Reco client. And in order to do so, we are going to need a couple of keys. We are going to need an access key, which I'm just going to set in none for now. And we're also going to need a secret key, which I'm also going to set in none for now, right? We are going to need these 2 keys in order to continue with this project, because we need to use these 2 keys in order to create a client, an AWS Rekognition client. Now, let's go back to my browser and let me show you exactly how to create these 2 keys. So let's go back to my AWS Management Console, and I'm going to show you super quickly how to create these 2 keys we need in this project. But first, obviously, you need an AWS account in order to continue, right? This is very, very important. And also, you need to log in into your account. Once you have an account, once you have created an account and you are logged into your account, you are going to see something like this. This is your AWS Management Console, and these are all the services which you have available in AWS, right? These are a lot. But in today's tutorial, we are only going to use only one service, which is IAM. So we need to type IAM over here, and we need to select this option. Then this is your IAM Management Console, and you need to select users. We are going to create a new user. Then you need to select add users. And we are going to choose a name for this user. I'm going to say something like AWS Reco tutorial, right? This is the name of my user. This is the user I'm going to create. Then you need to select attach policies directly, and we are going to search for Rekognition, right? And I'm going to select Amazon Rekognition full access. I click here, then next, and that's pretty much all. So I'm just going to create user. So the user is now created, and then I'm going to select the user over here, AWS Reco tutorial, and I'm going to security credentials, because now it's where we are going to create the 2 keys we need in our project. So we scroll down until this section over here, access keys, and create access keys. Then you can see that we have all these different options. And if I'm not mistaken, it's pretty much the same how you are going to create this access key. Pretty much absolutely all these options are going to create exactly the same keys, and you can just use it from your project, if I'm not mistaken. But we are going to use this one over here, which is local code, because this is the description which fits better to our project, right? You plan to use this access key to enable application code in a local development environment to access your AWS account. If I'm not mistaken, it's pretty much the same if we use any other option, but let's just use the option which fits better with our use case. And now you can see we have a warning over here, which is alternative recommended. Use an integrated development environment IDE which supports the AWS toolkit enabling authentication through IAM Identity Center. And this is very important because this is a warning we get from AWS, because it means there is a better way, or there is a more secure way to create these keys and to access this service. But in this tutorial we are not going to mind this warning, because it will involve to create a solution which it's only useful for a very specific IDE, right? In my case I'm using PyCharm, and if I follow these instructions I will be using a solution which is only useful for PyCharm, right? And I want to make this tutorial as generic as possible, and I want you to use it as well. So in case you're using a different IDE, let's just create these access keys in a different way, right? The only thing I'm going to do is I'm going to select this checkbox over here. I understand the above recommendation and I want to proceed to create an access key, and I'm going to click next, right? I'm going to show you a very, very generic way to use it, which is going to work for whatever your IDE is, right? If you use PyCharm or if you use Visual Studio and so on. So I'm not going to type anything here, so just create access key, and these are our access keys. Something that's very, very important is that access keys are very personal, and you should never disclose them with anyone in any situation, right? So you should never do something like I'm doing right now, right? Just making a video with my access keys completely available for anyone watching this tutorial. Never do something like this, right? In my case, it's not really that important because I'm just going to delete these keys once this tutorial is over, but please be super, super mindful and super careful with who has access with your access keys, with your private access keys, because this is very, very sensitive information. So the only thing I'm going to do for now is to copy these 2 fields. I'm going to start with this one, which is access key. I'm going to copy this field, and I'm going to get back to PyCharm. I'm going to my file, to credentials.py, and the only thing I'm going to do is to paste the access key over here, right? Then let's get back to this page, and I'm just going to copy the secret access key, and I'm going to get back to PyCharm. I'm just going to paste the secret key. And that's pretty much all. So these are the two keys you need in this project, and now we can continue with the main.py file, and we can just start coding our entire pipeline. So let's get started, and the first thing I'm going to do is to import both three, and let's import OpenCV as well, so we can just focus on everything else, right? So I have imported the two libraries we have installed in this project, and now let's get started by creating this AWS Reco client. And this is how we're going to do. I'm going to call this client Reco client, and this is something like bodo3.client, and then I need to input Rekognition. And then this is where we're going to input the access keys, right? So we're going to have two keys. One of them is AWS access key ID, and then the other one will be something like AWS secret access key, right? And now the only thing I need to do is to import credentials, and I need to import these two variables, right? So the first one will be something like credentials dot access key, and then the other one will be credentials dot secret key, and that's pretty much all. So now let's continue, and we're going to set the target class. So I'm going to create a variable which is target class, and this is where I'm going to define the class we are going to be detecting today. As I already told you, we are going to be detecting zebras. So now let's continue. Now it's time to load the video, and what I'm going to do is to go to my directory where I have the video, and I'm going to copy and paste this video to my directory where I have created this Python project. So now the video is located in this Python project, and it's called zebras.mp4. So let's go back to Python. So now let's load this video exactly by like this. I'm going to call cv2 video capture, and then this will be zebras.mp4, and this will be cap. Okay, now let's read frames from the video. So I'm going to define a variable which is read. I'm going to initialize it as true, and then while read, I'm going to read frames from the video like this. Read frame equal to cap.read, right? So we are reading frames from the video. And now let's convert this frame to JPG, and this is how we are going to do. I'm going to call cv2 im encode, if I'm not mistaken, then this will be JPG and then frame, right? And this is going to return two variables. One of them we are not going to use it, so it doesn't matter, and the other one is buffer. Okay, now let's convert buffer to bytes, and I'm going to do it like this. Let's call this something like image bytes, and this will be buffer 2 bytes, if I'm not mistaken, something like this. I'm not sure about this character. I'm just going to execute this file. I'm going to do it for only one frame, so we make sure everything's okay, and let's see what happens. Okay, and I got an error, and it says something like could not find encoder for the specified extension in function im_encode. Let's see if I have a character missing. I think it's .jpg. Let's see now. Now I have another error, which is object has no attribute to bytes. So I'm almost sure that this is without the underscore. Let's see now. And now everything is okay. Okay, so I'm just going to remove this break, and now it's the most fun part of this tutorial, because now it's the time to use Amazon Rekognition to detect objects in this video. So this is exactly how we are going to do. I'm going to call the client we have just created, Reco client, and I'm going to call detect labels. I'm going to input the image. We have just created this image byte, and this will be something like image. I'm going to open a dictionary, and this will be bytes and then image bytes, and that's pretty much all. And now I'm going to set the minimum confidence value in which we are going to, for which we are going to detect objects, right? We are going to set this value in 50%. So, and I think this is a capital M. And this means that we are only going to detect objects if the confidence value is greater than 50%. For everything else, we are not going to get the object, right? We are going to filter all the detections with a confidence value lower than 50%. That's exactly what it means. And this will be something like response, right? And now let's do it like this, okay? And now I'm just going to iterate for label in response labels, right? I'm going to iterate in all the results we got. So this is how I'm going to do. If label name equal to or target class, right? So if the object we have detected is a zebra, then we are going to iterate for instance number in range len label instances, and if I'm not mistaken, this is with a capital I, right? So we are going to iterate in all the zebras we have detected. And now let's continue. Now let's get the bounding box we have detected with this in this object, in each one of these objects. So this will be something like label instances, instance number, and then we need to call bounding box. Let's execute the code so far to make sure everything's okay. And let's see, let's do it for only one frame. So I'm going to break the loop here. Labels, right, because this is with a capital L most likely. Okay, everything's just fine. So I'm going to delete the break and I'm going to get back here and let's continue. So now I'm going to unwrap all the information in the bounding box. And this is something like x1 is equal to bounding box left, and I'm going to cast it to int. Okay, then y1 is equal to int bounding box top. Okay, then the width of this bounding box is equal to bounding box width with a capital W if I'm not mistaken, and then the height is equal to int bounding box height. And let's see what happens if we just execute, if we just print these values. So I'm going to print x1, y1, width and height. And also I'm going to remove the int for now, because for now let's just remove it so I can show you something, and then I'm going to add the int again, but let's just for now, to make sure everything is okay, I'm just going to execute this as it is. Okay, let's see what happens. Okay, you can see that these are the values we are getting, and this is why I removed the int. This is why I'm not casting to int, because otherwise everything will be a 0 or a 1. So these are the values we are getting, and everything is in relative coordinates. This is very, very important. So what we need to do now is to multiply these values for the width and the height of the frame we are reading, right? So I'm going to define two new variables, which are h and w. And these are the height and the width of every frame. So this will be frame.shape. And now let's just continue by doing something like this. So x1 will be bounding box left multiplied by the width of the image, right? Then y1 will be exactly the same, but for h by times h, and then this is times w, and this is times h. Okay, and now I'm going to cast it to int. Okay, and then let's print the values for x1, y1, width and height again, and let's see what happens. Okay, and now you can see that we are getting integers and everything seems to be okay, right? We are getting objects, we are detecting objects, so everything is okay. So then the next step of this pipeline is to write the detections. But before we do so, let's just make sure everything is 100% proper, everything is working just fine, and let's just visualize some of the frames with all the bounding boxes we are detecting on top, and let's see what happens. So I'm going to call cv2.rectangle. I'm going to input the frame and then x1, y1, and then x1 plus width and y1 plus height. And then I need to input the color, if I'm not mistaken, which is going to be green, and then the thickness of the rectangle, which will be 3 for now. So and then let's see what happens. I'm going to visualize this frame by calling imShow frame and cv2 wait key. Okay, so we are plotting a bounding box on top of absolutely every single frame. We are plotting a bounding box for each one of our objects, and let's see what happens. I'm just going to execute this file and let's see if we are detecting all of our zebras, and everything seems to be working just fine, right? If I just press a letter, you can see that we are just detecting all the frames. This is not running on real time because obviously we are detecting many zebras, and we are plotting a rectangle, a bounding box for each one of these zebras, so this is not running on real time, but you can see that nevertheless this is working just fine. So the only thing we need to do now is to take all these detections and we need to write these detections to our file system, to our computer. So this is how we are going to do. I'm going to remove all the plotting because we are not going to do it anymore. And now let's just write the detections. And in order to do so, I'm going to create a new variable, variable with the output directory, with the location of the output directory, which is where we are going to save all these detections. So I'm going to define this variable like output dir, and this will be my local computer, and the directory will be called data. So let's go back to the directory of this Python project and let's create a new directory which is called data. I'm going to press enter, and that is it. Now let's save all these detections into the YOLO format. So I'm going to create another directory which is images. I'm going to create another variable for the images directory, which will be something like output dir images, and this is us path join output dir and images, right? I'm going to import OS, and then I'm going to create another variable for the annotations, for the detections. I'm going to call this other variable ans, output dir ans, and this will be something like this. And now I'm going back to my local computer, to my file system, and within this data directory I'm going to create two additional directories, one of them for the frames, for the images, which I'm just going to call imgs, exactly how I have called this variable over here, and then I'm going to create another folder which is called ans, right? Exactly as I have called this other variable over here. So now everything is set, everything is ready. We have just created the directories where we are going to save all the data. Now let's get back over here, and the only thing we need to do is I'm going to do something like with open. I'm going to do it here before we start this iteration. It's going to be much better if we do it here. For every single one of these frames we are going to open a text file, and the path name will be something like with us path join output directory ands, and then this will be the file name, which I'm going to call frame.txt, and then I'm going to input the frame number, format frame number, which we haven't defined, so I'm going to define it in a second, but let's just say string frame number CEDA field 6, right? Now let me explain this in a couple of seconds, but for now let's just get here. I'm going to define a new variable, which is frame number. I'm going to initialize it as -1, and then I'm going to increment it for every single frame we read over here. Okay, so we are initializing in -1, we are incrementing this variable here, and then for absolutely every single image we are creating this file name, which is frame, and then this integer, this number, but with 6 zeros. We are filling this number with six zeros, so we make sure all the file names are all the same length. That's very important, or that's actually more for formatting reasons. It's not 100% needed, but it's going to make it look much nicer. So now let's just continue, and I'm going to open this as write, and then as if, and then that's pretty much all. Okay, and now for each one of our detections, the only thing we need to do is to write these detections, and this is how we are going to do f.write. We are going to write 5 numbers. Remember, we are going to do it in the YOLO format, so we need 5 numbers. And this will be something like, the first one of these numbers will be a 0, because we will be detecting only one object, which is zebra, so this will always be the number 0. Then it's the x and the y coordinates of the center of this bounding box, so this is something like x1 plus width divided by 2, and then it's exactly the same, but for the y coordinate. Plus height divided by 2. Okay. And then it's the width, and then it's the height, and I see there's an issue here. Okay. A parenthesis missing. Let's see now. Okay. And okay. Perfect. And if we are using the YOLO format, remember we are just converting all these values into integers, but if we are going to save the annotations into the YOLO format, we don't really need to do this conversion, right? So I'm just going to delete the integer and this multiplication. I'm going to do something like this, because remember how the YOLO format works. We need the coordinates into the relative. We need relative coordinates, so we with the values like this will be just fine. And that's pretty much all. Okay, so we are writing all the detections, and once we have reading all the detections, the only thing we need to do is to close the file. And that's pretty much all. And let's save the images as well. Let's just prepare this dataset as if it were a dataset in the YOLO format. So we can just take this dataset and we could potentially train a model. We could train an object detector with the data we are going to be saving. And in order to do so, we need to save the detections, but we also need to save the images. So I'm going to save the images over here. We can just do it after we save all the detections. We can call cp2 imwrite. Then the file location, which will be pretty similar to the detections, but we are going to change txt by jpg, and that's pretty much all. But we also need to change the directory, which will be images. Okay, and then we need to input the frame. And that's all. Okay, so let's see now if everything is okay. Let's just run it for only one image and let's see what happens. Everything is just fine, and if I go to my local directory, I open ANS, you can see I have a file with many detections, which makes sense because we had many zebras. And then if I go to the images directory, you can see I have a frame, the first frame from the video, so everything seems to be just fine. So the only thing we need to do now is to execute exactly the same process, but for absolutely all the frames. So I'm going to remove this break, and then let's see what happens. Okay, I see I got an error because we should be doing everything else only if we have read a frame, right? So this is a very small mistake. And also, while I was waiting for the execution to be completed, I realized another mistake, which is we should be dividing only the width and only the height by 2. These are the X and the Y coordinates of the center of the bounding box. Everything should be okay now. So, in order to be 100% sure everything is okay, I'm just going to execute this file again. Now the execution has been completed and we don't have any errors, so everything is just fine. And if I go to the images directory, you can see I have 755 images because we are starting from 0, so we have 755 images, and these are the images of our zebras, right? These are all the frames from the video. And then if I go to the annotations directory, you can see I have all my annotations, and I also have 755 files, right? We have 754 and we are starting from 0, so we have 755. So everything is working just fine. So this is exactly how you can use Amazon Rekognition as an object detector. This is exactly how you can detect objects using Amazon Rekognition, and this is going to be all for this tutorial. In this video, we're going to work with automatic number plate recognition, and this is exactly what you will be able to do with today's tutorial. You can see that we're detecting all the license plates in this video, and we're also reading the text from these license plates. We're using 100% Python, we're going to use an object detector based on YOLO V8, we are going to do object tracking, and we're going to read the text from these license plates using EasyOCR. So this will be an amazing tutorial. My name is Felipe, welcome to my channel, and now let's get started. So let's get started with this tutorial. Today we are going to work with automatic number plate recognition, and let me show you a few resources, a few repositories which are going to be super useful for today's tutorial. The first one is YOLO V8. Because we are going to be detecting license plates and then we're going to be reading the text from the license plates, right? And in order to detect our license plates, we are going to use an object detector which is based on YOLO V8. So YOLO V8 is going to be super important in today's tutorial, and I'm going to show you more details in a few minutes. But for now, let me show you the other repository which we are also going to use in this tutorial, and it's going to be super important, and it's SORT. It's an object tracking algorithm which is called SORT, because today we're going to do object detection and we're also going to do object tracking. This is going to be an amazing tutorial, and in order to do object tracking we are going to use SORT. And then once we have detected the license plates, once we have implemented all the object tracking, once we have done everything we need to do, we are going to read the content of the license plates using EasyOCR. So this is a Python library which is going to be super important in this tutorial. And now let me show you the data we are going to use in this tutorial. Let me show you the video we are going to use in order to test the automatic license plate recognition software we are going to use in this tutorial. You can see that this is a video of a highway, and we have many cars which are going through this highway. And the important thing about this video is that all the cars, we have like a very frontal view of absolutely all the cars, and most importantly we have a very frontal view of all the license plates, right? You can see that for absolutely every license plate we detect in this video, we have a very frontal view, and this is an ideal point of view to build a project like this. So this is exactly the video we are going to use in this project. And now let me show you something else. If I go to Google and I search for license plate and I go to images, let me show you something. You can see that we have a lot of diversity when it comes to license plates, right? We have many different types of license plates. We have some license plates which are comprised only with numbers, like this one. Then we have other license plates which are only letters, like these two. And we have many different examples. We have many different types, many different formats. I will say that absolutely every single country, absolutely every single state, absolutely every single time in history have its own license plate format, right? Its own license plate style, its own license plate system, right? There are many different types of license plates. There's a lot of diversity when it comes to license plates, and obviously it's very challenging to build an automatic license plate recognition software to deal with absolutely every single type of license plate, right? I'm not going to say it's impossible. It's not impossible, but it's a very challenging task. So in order to make it more simple, in order to simplify our problem, we are going to focus only on one very specific type of license plate, which is this one. We are going to be working with the United Kingdom license plate system, with the United Kingdom license plate format, which is comprised of 7 characters. The first 2 characters are letters, then we have 2 numbers, and then we have 3 more letters, right? So we have 2 letters, 2 numbers, and 3 letters, and this is the exact structure of the license plate type we are going to be working today in this tutorial, right? This is the exact same type we are going to be detecting with the software we are going to build in this tutorial. But today I'm going to show you a very generic process and a very generic pipeline. So by making some adjustments into the code we are going to be making today, you will be able to apply the same process to other types of license plates, right? We are going to work with this type in this project, but you will be able to make some adjustments in everything we're going to be doing today, so you will be able to apply the same process to other types of license plates, right? So that's something I'm going to show you better in a few minutes, but for now let's continue. Now let me show you something else. When we were starting this tutorial, I showed you that we were going to use an object detector based on YOLO V8 to detect license plates. Now let me show you the data I used in order to train this license plate detector, right? This is exactly the dataset I used in order to train this detector. And I'm going to give you a link to this dataset in the description of this video. And if you want to know exactly how I trained this object detector, I invite you to take a look at one of my previous videos where I show you how I trained an object detector using YOLO V8. In that video is the step-by-step guide of how to train an object detector using YOLO V8, and that's exactly the same process I followed when I was creating this license plate detector. So this is the data I used, and if you want to know exactly how I trained that object detector, then just take a look at the video I'm going to be posting over there, right? So now let's continue. I already showed you all the resources we were going to use in this tutorial. I already showed you the type of license plate we are going to be detecting today, and now it's time to go to PyCharm so we can start implementing all the code of today's tutorial. And now let's go to PyCharm. Let's go to this PyCharm project and let me show you some files I have over here. You can see I have many different files, and for now let's just focus on these two, main.py and util.py. Main.py is the file in which we are going to be coding the entire pipeline of this tutorial, right? You can see that this is a sequence of steps which we are going to follow in order to build this automatic license plate recognition software. You can see that the first step is loading the models, then loading the video, then we're going to read frames, and so on. This is the entire pipeline, the entire process we are going to be building today. And then we have this other file, which is util.py. In this utils file, we have 5 functions. Let me show you. These are the functions we have defined over here. And from all of these functions, we are going to focus on these 2, which are read license plate and get car. These functions, if I open these functions, you can see that they are completely empty, right? We need to implement these functions in this video, and then the other 3 functions, they are already implemented, right? Everything is ready and we're just going to use them. And the idea is to focus on these 2 functions over here, because these 2 functions are way more important from a computer vision point of view, right? So these are the functions we are going to focus the most, and this is the util.py file. Now, if I go back to main.py, now it's time we start with this process. Now it's time we start with this pipeline. And in order to do so, we are going to start importing YOLO. So I'm going to say from Ultralytics, import YOLO. And then we are going to load the models. That's the first step in this process. And the interesting part is that we are going to have 2 models, because we are going to be detecting license plates, but we are also going to be detecting cars. That's going to be a very important part in this process. So I'm going to be loading 2 models. I'm going to call the first one of these 2 models Coco model, because this is a model which was trained on the Coco dataset. And this is going to be YOLO, and we're only going to use a pre-trained model from YOLO v8, which is YOLO v8 nano.pt, right? We are just going to call this pre-trained model, and this is one we are going to use in order to detect cars. It's very important we detect cars. I know we are going to detect the license plates and we are going to read license plates, but detecting cars is going to be super important, and you're going to see exactly why in a few minutes. Then we're also going to load the license plate detector, and we're going to call it license plate detector. And this is going to be YOLO, and we need to input the path to this license plate detector, and the license plate detector is located in a directory which is called models, and it's called license plate detector.pt. So I'm just going to models. Okay, now it's time to load the video we are going to use today, and in order to do so, I'm going to import CV2, and I'm going to call CV2 video capture, and I'm going to input the video location, which is something like the current directory, and it's called sample.mp4. Okay, and this is going to be cap. Okay. Now we are going to read frames from the video, so I'm going to define a variable which is read, and I'm going to initialize it as true, and then while read, I'm going to read frames from the video like this: read frame equal to cap.read. If read, then I'm going to continue. Okay. And this is going to be pretty much all for now. So we are reading frames from the video, and now it's time to continue detecting all the vehicles, right? We are going to be detecting all the cars, and therefore we are going to be detecting the vehicles. And in order to do so, this is where we are going to use the first model, which is the model trained on the Coco dataset. So we are going to do something like this. I'm going to call Coco model, and I'm going to input the frame, and this is going to be results, right? I'm going to call this object detections, and in order to move one step at a time, I need to access the first element, and in order to input one step at a time, I'm going to print detections, and I'm only going to execute the first 10 frames, otherwise it is going to be very this is going to take a lot of time. So, and frame number lesser than 10, and obviously I need to define a variable which is frame number. I'm going to initialize it in -1, and then I'm just going to increment it here. Okay, and I don't really need the pass anymore, and let's see what happens if I print detections. Okay, so everything seems to be working just fine. This is all we got. And you can see that this is a lot of information. These are all of our detections. So everything seems to be working just fine. So what I'm going to do now is we are going to iterate for detection in detections. And this is going to be for detections.boxes.data.toList. And let's print detection again, so we know exactly how this looks like, and we know how to access all the information. Okay, so this is how each one of our detections looks like, right? You can see that we have 1, 2, 3, 4, 5, 6 numbers, and the way this works, this is going to be something like x1, y1, x2, y2. Then we will have the score, and then we will have the class ID, right? This is detection. So remember, we are using a model which was trained on the Coco dataset, so we are detecting many different objects, right? This is the class ID. This is exactly the type of object we are detecting at every single time, at every single one of these detections. So this is very important, and then we have the confidence value, right? This is how confident our object detector is of this specific detection, and then this is the bounding box, right? So we have x1, y1, x2, y2, the bounding box, then the confidence score, and then the class ID. And something that's very, very important, we are doing all of this in order to detect vehicles. So as the Coco dataset, as this model which was trained on the Coco dataset is detecting many, many different objects, we are going to say something like this. If int class ID in vehicles, then we are going to continue. And vehicles is a variable which we haven't defined, and we are going to define it with the indexes, with the class IDs of all the vehicles in the Coco dataset. This is a list of all the objects which we can detect using this model, right? You can see that these are a lot of objects, and some of these objects are related to vehicles and some other objects are not. For example, you can see we have person, bicycle, car, motorbike, airplane, bus, train, truck, and so on, right? So from all this very, very long and very comprehensive list, we are going to make sure we are detecting a vehicle. So we are going to say, if the class ID we are detecting is either a car or a motorbike or a bus or a truck, then we are going to continue. And if not, we are going to neglect the bounding box, the detection we just got. And the indexes we are interested in are 0, 1, 2 for car. So we are just going to put 2. Then 3 for motorbike. 4, 5 for bus. And then 6, 7 for truck, right? We don't really have any motorbike in this video, I know for sure because I already watched the video, but nevertheless, in order to make this more generic, I'm just going to add motorbike as well. So if our class ID is within our vehicles, then we are going to continue. And I'm going to create another variable which is detections underscore, and this is where I'm going to save all the bounding boxes of all the vehicles we are going to detect in this video. So I'm going to do something like this. If we have detected a vehicle, then I'm going to append the bounding box and the confidence score to this new variable. And please mind that I'm not saving the class ID. From now on, it's not really that important. We are not really going to care about the specific class ID we have detected. From now on, the only thing we care about our detections is that they are vehicles, right? And we don't really care to know exactly what type of vehicles. So this is the new variable in which I'm going to be working from now on in this tutorial, in this process. And now let's continue. And now it's the time in which we are going to implement the object tracking. Remember, we were going to work with object tracking in this tutorial, and now it's the time where we are going to implement this tracking functionality into this project. And before we do so, let me give you a very quick explanation regarding why exactly we are using this tracking, why exactly we are going to implement this object tracking. And basically, every time we solve a problem, every time we solve not only a computer vision problem, but any type of problem, you need to use absolutely all the information you have available regarding that problem. And in this case, we are going to be tracking license plates which are moving through a video, right? We are going to be detecting license plates on individual frames, and these license plates are objects which are moving through a video. So if we are able to track these license plates through all this video, we will have more information, and this additional information is going to be super valuable in order to build a more robust solution. So that's pretty much the reason why we are going to implement this object tracking. And we are going to be tracking, we're not going to be tracking the license plates themselves, but we are going to be tracking the cars, the vehicles. And I'm going to show you exactly why later on. So this is what we are going to do. We are going to work with this repository. Remember, I showed you this repository when we were starting with this tutorial. And the first thing you should do is cloning this repository into your local drive, into your local directory. You need to clone this repository into the directory, into the root directory of your PyCharm project. So in my case, this is the root directory of my PyCharm project. This is where I have all my Python scripts, and this is where I have all my files related to this project. And you can clone this repository in one of these two ways. Let me show you. One of the ways is opening a terminal and type in something like git clone and the repository URL. So I'm going to click here, I'm going to copy the repository URL, and then I'm going to paste the repository URL here, and then the only thing you will need to do is to press enter, right? And that's exactly how you can clone this repository into your local computer. But there's another way in which you can do it, and actually this is a much more simple way, and maybe you prefer to do it like this, which is just downloading the entire repository as a zip file. And once you have downloaded this file, this zip file, the only thing you need to do is to copy and paste, is to take this directory, this sort master directory, into your local directory, right? That's the only thing you need to do, is to drag and drop this directory into your local computer, and that's it. And please mind that this directory is called sort master, but you will need to edit the name, you will need to rename this directory into sort, right? You can see here in my computer, this is my directory, this is called sort. If I open this directory, you can see these are all the files which are in this repository. So basically remember to rename this directory into sort. It's going to be called sort master, but you need to rename this directory into sort. That's very, very, very important. Otherwise, you will have some issues, possibly you will have some issues with the next steps in this tutorial. So let's go back to PyCharm. This is the repository you need to clone into your local directory, and remember to call the directory containing this repository, remember to call this directory sort. Now let's take it back to PyCharm, and what I'm going to do now is just importing sort. Let's call from sort.sort. I'm going to import everything. We are going to import absolutely everything from this library, and then I'm going to call an object. I'm going to create a new object which is called mod tracker, and this is going to be equal to sort. Right? This is the object tracker we are going to use in order to track all the vehicles in our video. And now let's get back here, and what I'm going to do now is just calling modtracker.update, and I'm going to input a numpy of this list we have created containing all the vehicles in our video, right? And this is going to be something like track IDs, right? So track IDs is going to contain all the bounding boxes of all the vehicles we have detected in this frame, but with the tracking information, right? It's going to add an additional column, an additional field, which is going to be the car ID, the vehicle ID for each one of the cars we are going to detect. And this vehicle ID or this car ID is going to represent that specific car through all the video, right? So let's continue. So now we are tracking all of our objects, all of our cars, and now it's the time to detect the license plates, right? So far the only thing we have detected is the cars in the video, but now it's the time to detect the license plates, and in order to do so we are going to use this detector over here, which is license plate detector, and we're going to do it exactly the same way as we have detected the cars, right? I'm just going to copy and paste this sentence, and I'm going to replace Coco model by license plate detector, right? And this way we are going to be detecting all the license plates. I'm going to call this object license plates, and then I'm going to iterate in all the license plates we detect within this frame, and in order to do so I'm going to call for license plate in license plates dot boxes dot data dot to list, and that's pretty much all. And then let's unwrap all the information we got from this license plate exactly as we did before. So this is going to be something like x1, y1, x2, y2, score, and class ID. This is going to be license plate. Okay, then we will need to assign each license plate to a given car, right? Because we have detected all the cars in every frame and all the license plates in every frame, but so far we have cars and we have license plates and we don't really know which license plates belong to which car, right? And we know for sure that every single license plate will be on one of our cars, but we don't really know which one goes with which one, right? So now in this step is where we are going to assign a car to absolutely every single one of our license plates, right? And in order to do so, we are going to use one of the functions in our util file. We are going to use this function, which is getCar. This function receives a license plate and receives this object we have over here, receives all this object with all the tracking information for all the cars in that specific frame, and it returns a tuple containing the vehicle coordinates and its ID, right? So we are going to call this function getCar, and this function is going to return the car this license plate belongs to, right? This is what we're going to do. I'm going to import from util import getCar, and now I'm going to call getCar. I'm going to input the license plate, and I'm going to input this object, which is track IDs. Remember, this object contains all the bounding boxes and also all the tracking related information, right? That's very important. And the return will be the coordinates of the car this license plate belongs to. So this is going to be something like X car 1, Y car 1, X car 2, Y car 2, and then the car ID for this car, right? Remember, every single car in our video will have an ID. It will have a very unique ID, which is going to identify the car through all the frames in the video. That's very important. And also please mind that this function is completely empty for now, right? This function is only returning some very dummy values, and this function is completely and 100% empty, and this is exactly what we will need to implement in the next step in this project, right? Once we are completely ready, once we have completed this pipeline, then at the end of this pipeline, at the end of this process, then we are going back here to util.py, to this file, to the util.py file, and we're going to implement this function, right? So now we have assigned the license plate to a very specific car. Now we know what's the car this license plate belongs to, and now we can continue with the next step, which is cropping the license plate. And this is how we're going to do. We are going to call frame, and then we're going to input the license plate coordinates, which is int y1, int y2, and then int x1 and int x2, right? So this is the license plate crop, and that's pretty much all we need to do in this step of this process. And now let's continue to the next step, which is processing this license plate. Right now we are going to apply some image processing filter to this crop we have over here in order to further process this image, so we improve this image so it's much simpler for the OCR technology, for easy OCR, to read the content from the license plate. Now it's time to apply some image processing filters to this crop. And specifically the filters we are going to apply are a grayscale conversion, and then we are going to apply a threshold. So let's see how we can do that. I'm going to call cv2.cvt color. I'm going to input the license plate crop, and then I'm going to call cv2 color bgr to gray. And this is going to be license plate gray. License plate crop gray, right? Now we have converted the license plate crop into a grayscale image, and now the only thing we need to do is to call cv2 threshold. We are going to input this grayscale image. Then it's the threshold, which I'm going to set in 64, and then it's the value at which we are going to take all the pixels which are lower than the given threshold, right? Which is 255. And then I say the value at which we are going to take all the pixels which are lower than the threshold, because we are going to use the inverse threshold. We are going to use the trace binary inverse type of threshold, and this type of threshold is going to take all the pixels which are lower than 64, is going to take them to 255, and all the pixels which are higher than 64 is going to take them to 0, right? That's exactly how this threshold works. And if you want more details on how this function works, I invite you to take a look at one of my previous videos where I show you an entire course of OpenCV with Python, and one of the lessons in this course is exactly about thresholding, right? It's exactly about this function. So I'm going to be posting a link to this course somewhere in this video, so you are welcome to take a look at this course and at this lesson particularly to get more details on how thresholding works. Now let's continue. This is going to be equal to a variable which we are not going to use in this tutorial, so it doesn't really matter. And then I'm going to call the output license plate crop threshold, right? So this is going to be the thresholded image, and this is exactly the image we are going to input into our OCR technology, into our easy OCR algorithm. And in order to be more clear about the difference between these two images, I am going to visualize these images super quickly so you see exactly how they look like. I'm going to call imShow, and I'm going to input this image, which is license plate crop. I'm going to call this window crop. I'm going to call it original crop so it's more clear. This is the image we are cropping from the frame. And then I'm going to call cv2 imShow again, and in this case I'm going to be plotting the threshold, and I'm going to input this other variable. And then the only thing I'm going to do is to call cv2 wait key. And let's take a look at these two images super quickly so you see exactly how they look like. And this is what we got, and you can see that this is the frame, this is the crop we are making from the frame. So this is the license plate, and this is exactly how we are cropping this license plate from the frame, and this is the thresholded image, right? You can see that in this image absolutely every single pixel is either white or black, and this type of image, this thresholded image, will make it much simpler to easy OCR, to our OCR technology, to read the content from this image, right? This is the image we're going to use in order to read the license plate number, because this is going to make it much simpler to easy OCR. So it's going to be much simpler to our OCR to read the license plate. So that was like a very quick way to show you how these two images look like. And now let's continue. Now it's the time to read the license plate number. We are almost there. We have almost completed this process, and this is how we're going to do. Now we're going to call another function which is defined in util.py, and this function is read license plate. And you can see that this function is not implemented either. This function is completely empty. We are returning some dummy values, and this is another function which we are going to implement later on. We are going to implement after we are happy with this process. Once we are completely and absolutely happy with this pipeline, then we are going to move to util.py and we are going to implement this function as well. But for now, we are just going to use this function. So I'm going to import it as well. No, this is not the function name. Read license plate, something like this. And now let's see how we can use this function. I'm going to call util.readLicensePlate, and this is going to return two values. Let's look at the function documentation to see exactly what are the values which are going to be returned here. We are going to, it's going to return a tuple containing the formatted license plate text and its confidence score. So this is going to be something like license plate text and then license plate text confidence score, right? These are the two values we are going to be getting from here, and the input should be the license plate crop. In our case, we are going to input the thresholded crop, right? This thresholded version of our crop, and that's pretty much all, right? Remember, we are just completing the pipeline, the most generic process. Then we are going to get back here in order to implement this function and this other function, right? And now let's continue. Now the only thing we need to do is to write the results. We are almost there. We have almost completed this process, and now obviously if we want to take these results and we want to visualize these results, or if we want to analyze these results, whatever thing we want to do with these results, we obviously need to write these results to our local computer. So this is how we are going to do. In order to write these results, we are going to use another function which is also defined in this util.py file, and it's called write_csv. And this function is implemented. This function is 100% and fully implemented. You can see that this is all the code we have for this function, and everything is just ready, and we can just use this function as it is. Remember, in this tutorial and in basically all my tutorials, we always focus on the computer vision part of the problems. So writing this CSV file is not really that important from a computer vision point of view, so that's why we are not really going to implement this function live in this video, but this is already implemented and we're just going to use it. So let's see what this function does, and it says writes the results to a CSV file, and it receives two arguments, which are the results, which is a dictionary containing the results, and then it also receives a path to the CSV file we are going to produce, and this is going to be the path in which we are going to write this CSV file, right? It's the path in which we are going to save the CSV file we are going to produce. So if we are going to input a dictionary, then we need to produce a dictionary in order to input into this function, right? We need to take all of our information and we need to put all of this information into a dictionary, right? That's very, very important. So that's what we are going to do now, because for now the only thing we have done is just computing all the information, but we have not saved this information into any type of dictionary or anything like that. So I'm going to create a new variable which is called results. And results is going to be a dictionary, and then this is where I'm going to save all the information, and this is how we are going to do. The first key in this dictionary will be the frame number, right? We are going to save all the information, and we are going to start with the frame number. We are going to have a different key for absolutely every single frame in our video. And then for absolutely every single frame, we are going to save all the information which is related to all the cars we are detecting, and most importantly, to all the license plates, right? So then I'm going back to the end of this pipeline here, and I'm going to say something like, I'm going to make a very quick edit first, which is going back to this function, and instead of returning two nons, I'm going to be returning two zeros, right? Because we are going to reserve this other output, we are going to reserve the non output for those times in which we are going to find an error, or we are going to have any type of issues reading the license plate, and this is going to be much more clear later on once we are implementing this function. But for now, just bear with me that it's much more convenient to return some dummy values which are different than none. So let's get back here, and this is where we're going to say if license plate text is not none, we are going to save all the information about this license plate in this dictionary we have just created. So we are going to take this variable over here, which is results for that specific frame number, and we're going to create a new entry with all the information for the license plate we have detected, right? And this is how we're going to do. I'm just going to write it first, and I'm going to explain it once it's done, once I'm completed, and this is what I'm going to do. I'm going to say the next key is the car ID, right? This is going to be results, frame number, car ID, and then for this car, I'm going to create a new dictionary, which is going to have two keys. One of them is car, and the other one is license plate. For car, we are going to have another dictionary, which is the bounding box, and that's it, right? And for the license plate, we are going to have another dictionary, which is something like box, the bounding box. Then also the text we have detected, then the confidence value for the bounding box, and then the confidence value for the text, right? Okay, and that's pretty much all. So I'm just going to format this a little nicer. And that's pretty much all. Now let's see what exactly we need to input in each one of these fields. Okay, so basically for the car bounding box, we are going to input these values over here, which are the car bounding box, right? These are the coordinates of the bounding box of this specific car. And then for the license plate bounding box, we are going to input these values, which are the coordinates for the bounding box of this license plate. And then for the text, we are going to input this value, which is license plate text. For bounding box score, we are going to input this value, which is the score in which we have detected this license plate. Then for text score, we are going to input this variable, which is license plate text score. And by doing so, we don't have any errors and everything is okay. So for every single frame number, we are going to be saving all the information which is related to each one of our cars. And all the information for each car will be the information of that specific car, where the car is located, and then all the information about the license plate which we have detected in that specific car, right? And for the license plate, we are going to save all the information we have, right? And we're going to save all this information only in those cases in which we have detected a license plate, and every time we have successfully read the license plate number from this license plate, so this object is not known, we are going to be saving all this information into this dictionary only in that case, only when we have detected a license plate and when we have read its license plate number, right? And please notice the structure I have built for this information, for this dictionary, because remember, every time we detect a license plate, it will not be floating around in space completely isolated. No, that will never happen. Every time we detect a license plate, it will be on a given car, and this car will be on a given frame, right? So this is exactly why this structure I have decided for this dictionary. And once we have created all this information, the only thing we need to do is to call. I'm going to import this function as well. I'm going to input, the name was something like writeCSV. So let's import writeCSV as well. And something is going on because we are not really using this import we have over here. So if I scroll down, I see I'm not really importing the function itself. I think there we should be okay. Okay. So now let's go back here, and I'm going to call this function, which is writeCSV, and I need to input the dictionary. So I'm going to input results, and I'm also going to input where I want this CSV file to be saved. And I'm going to save all this information into a CSV file called test.csv. So what I'm going to do now is I'm going to execute this pipeline, I'm going to execute this process as it is, and then we are going to take a look at this file, and then we are going to continue, right? Then we are going to see if the file we are going to create, it makes sense, right? So I'm just going to press play. Okay, the execution is now completed, and now if I go to my local directory, to the directory of this PyCharm project, this is test.csv, so this is the file we have just created, and if I open this file, you can see that this is all the information we have saved and we have extracted from this video, right? Remember, we are processing only the first 10 frames, we are still processing only the first 10 frames. So this is all the information we have extracted so far. And please remember, we are just computing some dummy values from some of our functions. So this is not really all the information. This is all the information we have computed so far. But other than all of these zeros over here and these zeros over here, you can see everything looks pretty well, right? We are just producing an entire CSV file with all the information we have computed from this video. We are almost there. And actually, we are there. We are ready. We have completed this pipeline. We have completed this process. We are almost there. The only thing we need to do now is going back to util.py because we need to implement these two functions, get car and read license plate. And once these functions are implemented, then we are going to be producing a real file, right? We are going to be producing a file with the entire information here and here, right? We are going to be producing the real license plate number and the real license plate score, and also the car bounding box and the car ID for absolutely every single license plate in absolutely every single frame in which we have a detection, right? So we are almost there. I am super excited. And now let's continue to the util.py file so we can implement these functions. And let's start with get car. Remember, from the main.py pipeline, we were using this function, which is getCar, in order to assign which car each license plate belongs to, right? We had many cars and many license plates, and for each one of these license plates, we want to know what's the car this license plate belongs to. So this is exactly where we were using this function, getCar. And now let's see exactly how we are going to implement the function. And in order to do so, I'm going to show you a few pictures. This is a random frame from our video, right? You can see that this is a frame. We have many cars, and this is only a frame from the video. Once we have detected all the cars, we are going to have a situation like this. We are going to have many detections, because at every single frame we are going to have many cars. I don't know how many cars we have in this picture, but they are many. They are something like, I don't know, 20, 30, 50, maybe 60 cars. They are many cars. So for every single frame, we are going to have many detections, which are going to be our cars. We are going to have many bounding boxes for all of our cars. And also at every single frame, we are going to have all of our license plates. But please focus, please mind that we are only going to have maybe 1 or 2 or 3 license plates for every single frame, right? So we are going to have many cars, but only a few license plates. And the idea is to know which car this license plate belongs to, and the way we are going to know that is by looking at all of these bounding boxes, by looking at all of these cars, and by finding the car which contains the license plate, right? By finding the bounding box of the car which contains the bounding box of this license plate, right? That's the way we are going to find what's the car which belongs to this license plate. So that's exactly the idea of what we are going to be implementing in this function. Now let's see exactly how we can do that. The first thing I'm going to do is unwrap all the information in license plate. So in order to do so, I'm going to do something like this, because this is exactly the same object, license plate. So I'm just going to do this, okay? Then I'm going to iterate in all the cars we have over here. I'm going to say for, let's say for J in len vehicle track IDs, we are going to be iterating in all the cars we have detected. And remember, this is the entire information. This is the bounding box, and this is also the car ID. Remember. So now we are going to unwrap all the information for each one of these cars, and this is going to be something like X car 1, Y car 1, X car 2, Y car 2, and car ID. This is exactly the information which is in each one of the elements of this object vehicle trucks IDs. And this is vehicle truck IDs J. Okay. So that's pretty much all. We are iterating in absolutely all the bounding boxes of all the cars we found in this frame. We are iterating in all these bounding boxes. For each one of these bounding boxes, we are going to verify if it contains the license plate, right? That's exactly what we are going to verify, and this is how we're going to do it. We are going to see if x1 is greater, remember x1 is the upper left coordinate of the license plate, if x1 is greater than x car 1 and y1 is greater than y car 1, right? We are verifying that this coordinate over here it's greater than this other coordinate over here. We are trying to verify if we meet this condition, right? And then the other condition we need to meet is if this point we have over here, these coordinates we have over here, they are lesser than this other point we have over here, right? We need to meet these two conditions, and this is exactly how we're going to do it. If x1 greater than x car 1 and y1 greater than y car 1 and x2 lesser than x car 2 and y2 lesser than y car 2, then we have found the bounding box this license plate belongs to. We have found the car on which this license plate is located, right? That's what it means. If we have met all of these conditions, that's what it means. So in this situation, we are going to, I'm going to define a new variable, which is founded. And founded is going to be false at the beginning, and then it's going to be true in this case. And in this case, we're also going to break the loop, right? And then I'm also going to define another variable, which is going to be car index, and car index will be j. Okay, now if founded, then return this value, which is going to be okay. So if we have found the car which contains this license plate, then we are going to return these values, which are the bounding box of the car and also the car ID. And in any other case, we are just going to return this output. And in order to make it more clear that we have not found the car, we are going to return something like this, so it's going to be much more clear. So that's pretty much all. That's it. We have implemented this function, which is get car. And now let's continue. So now let's see if everything works well. Now we should have the right values for all the cars we are detecting, and the only thing I'm going to do is I'm going to execute this script again, and let's see what happens. Okay, I got an error, and I think I know what's the problem. I think we need to iterate in range len vehicle track IDs, and now everything should be okay. Let's try again. Okay, now it's completed, and now let's see the new file we have created, the new test.csv file. And now you can see that we have some values for car ID, and we also have some values for the car bounding box. So we are moving one step at a time, but we are making progress, right? So now let's continue with the util.py file, and now let's move to the next function, which is read license plate. Now it's time to implement this function over here, and something I'm going to do first is I'm going to do an if over here, and I'm going to continue with this pipeline only if car ID is different than -1, right? And now let's continue and let's see how we can implement this function, which is read license plate. And the only thing we need to do is to call ECOCR, and let's see how we can read the license plate. And let me show you some variables I have defined over here. These variables are going to be super important. Now these variables are going to be super amazingly important. You're going to see exactly why. And then also let me show you this reader we have here. I have already defined, I have already initialized this OCR reader, and you can see that I'm calling EasyOCR, and then I'm calling this method which is reader. So the only thing we need to do now is calling reader dot read text, and I'm going to input the license plate crop, and this is going to be detections. Then I'm going to iterate for detection in detections, because remember we could be detecting many different objects, many different text objects in this image. So for each one of these objects we are going to unwrap these objects first, and this is going to be something like bounding box, text, and score. This is going to be the detection, right? Each one of these detections is going to be something like the bounding box of the text we have detected, then the text we have detected, and then the confidence value for which we have detected this text. And then we are going to convert this text to uppercase, and we are going to remove all the white spaces, right? This is exactly how we are going to do, and this will be equal to text. Okay. And now it's the time in which we are going to use this format, right? Remember when we were starting this tutorial, I told you we were going to focus on this very specific type of license plate, right? We are going to work with this type of license plates. Each license plate is going to have 7 characters. The first 2 characters are going to be letters, then 2 numbers, and then 3 letters. This is the format of absolutely every single license plate we are going to be working with in this tutorial. So we are going to make sure every single text we detect complies with this format. And in order to do so, I have already created a function which is license complies format. This function returns a Boolean value, which is pretty much the verification of if this license plate complies with the format or not. We are going to be verifying if we have 7 characters, and we're also going to be verifying the first 2 characters are letters, and then the second, the third and the fourth characters are numbers, and then the last 3 characters are letters again, right? This is exactly what we are doing with this function, and this is a very important function we are going to use now. So let me show you exactly how we are going to use this function. If license complies format text, then, and only then, we are going to return the text and the confidence score. We are going to return these 2 values, these 2 variables, which are text and score, right? Only if the text complies with the format we are asking absolutely all the license plates, right? Only in this case we are going to be returning these values, and in any other case we are going to return none, right? This is very important, and this is going to make our solution way more robust and way better. And something that makes the solution even better is that we are not going to return the text on itself. We are going to call another function which is format license, and let me show you exactly what we are going to be doing with this function. I'm going to call format license text, and let me show you let me give you the idea, the high level idea behind this function. Sometimes when we are using an OCR technology, when we are using a library like EasyOCR, sometimes it's very challenging to tell some characters apart. For example, it's very challenging to tell a 5 apart from an S, right? You can see that the letter S and the number 5 are very similar, and it's very challenging for an OCR to tell the difference between these 2 characters. And we are going to have exactly the same situation for the letter I and the number 1, or for the letter O and the number 0, for example, right? Those are characters which are very hard to differentiate. They are very hard to tell apart. So This function I have over here, format license, the only thing it does is goes through all the characters in the license plate in the text, and for each one of these characters it fixes whatever issue we may have with this type of confusions, right? If, for example, we are reading this character over here and OCR, easy OCR, the OCR technology we are using, it says is the letter S, we know for sure it's not the letter S because we are expecting a number here. So if we have detected the letter S, then we convert this value to the number 5. And the same happens here. If we are reading this value, this character, and we are getting the number 5, we know for sure, for a fact, that that's not the number 5 because we are expecting a letter here. So we are going to convert the number 5 into the letter S. That's exactly the idea, the high level idea of what we are going to be doing with this function. We are going to be going through absolutely all the characters in the license plate, and for each one of these characters we are going to be fixing this type of issues in case we find any type of issues like this. And that's pretty much all. And I invite you to take a look at these two functions, to format license and to license complies format, and to take a much closer look and to properly understand exactly how they work, right? That's your homework. That's your homework from this video, so you properly understand how they work. So now let's continue, and now we are returning format license text and score if our license complies with our format, and we are returning none in any other case. And we are done. We are completed. Now we have completed our process. Now let's see what happens. Now I'm going to execute this file again and let's see what happens. I'm going to make a very small change. I'm only going to execute it for 10 frames, but I'm going to do it like this. If read, then if frame number greater than 10, then I'm going to break the loop. This is going to be much better. And now let's see what happens. I'm going to execute main again. Okay, it seems I have a typo over here. This is obviously not remove, but this is replace. I got confused because I was removing the white spaces, but this is obviously not the name of the function we want to use here. So now let's see what happens. Okay, now the execution has been completed, and now we have produced a new test.csv file, and if I open this file, you can see that we still have all the information related to the car ID and the car bounding box, and now we have all the license plate numbers we have read from the frames from the license plates, and also the confidence score for each one of these license plates. So we made it. We have completed this process. Now we are completed. We are done. So everything is ready. The only thing I'm going to do now is to execute this script, execute this main pipeline for the entire video. So I'm just going to remove this break over here, and that's pretty much all. And now I'm going to press play again, and then I'm going to show you how to visualize this data so everything looks like the video I show you in the intro. So let's see what happens. And now let's go back to PyCharm so I can show you exactly how you can create a visualization as the one I showed you when we were starting this video. And in order to do so, this is where we are going to use these two files, visualize.py and addmissingdata.py. And you're going to find these two files in the GitHub repository of today's tutorial, so you can just go ahead and use them in your project. And before using these two files, let me show you something first. If I go back here to the test.csv file we have created, let me do something. I'm going to filter by car ID, and I'm going to show you all the data, all the information we have extracted for only one of our cars. I'm going to select only the car ID number 3, right? This is only a random car ID in our data. You can see that all the frame numbers we have detected for this car ID are not consecutive. So this means that we have detected the number 0, the frame number 0, then the number 1, then it jumps to the number 4, then it jumps to the number 9, then 12, 13, 14, 15, 16, 17, then 27. So we have many missing frames, right? For some reason, we don't have the information for this car ID for many frames which are in between these two, for example, right? We don't have the information for the frame number 2, the frame number 3, or the frame number 5, 6, 7, 8, 10, 11, right? There are many missing frames for this car ID. So that's something that's going on. And remember that we are not saving all the information, because we are only saving the information for those license plates for which we have detected the car, the license plate it's on, right? The license plate, the car in where the license plate is located. And also we're only saving the information, the license plates for which we have read a license plate number which complies with our format, right? So we are not saving all the information. There's a lot of information which we are not saving into this CSV file. Remember how the OCR technologies usually work. I mean, they are very good, they perform very good, but in some cases they have errors, they have mistakes. So if in some cases they are not reading a number which complies with this format, then we are not going to be saving the information for those frames. So that's the reason why we have some missing frames over here. That's the first thing I want you to notice. Then another thing which is going to be much more important is take a look what happens with the license plate numbers. Now we have read the license plate numbers in all of these frames, and we have read a number which complies with our format, so everything is okay. But you can see that we have many numbers, right? For example, we have many different values, many different numbers. If I show you the number we have detected in the first frame, it's different than the one we have detected here in the frame number 4, right? And then if I continue scrolling down, you can see that we have also detected other values. For example, here, this is different. And if I continue scrolling down, this is also different. Here we have an N, we have a P. So for every single car ID, we are going to have many different values for the license plate. And this is a huge issue. This is a very important thing we need to solve, because obviously every single car has only one valid value for its license plate. So if we have so many values, if now we have so many values for the license plate, how do we make a decision? How do we know what's the real one, right? What's the real value, the most accurate value for the license plate? How do we make a decision? What's our criteria? That's a huge problem, and this is exactly where the object tracking is involved, because for every single car in the video, because we are going to be tracking the car through all the different frames in the video, for every single car we are going to have the value for the license plate we have detected in that given frame for that car. So if we want to know what's the value for the license plate of a given car through all the frames in the video, the only thing we need to do is to select the license plate we have read, we have detected with the highest confidence score, right? You can see this column is the confidence score in which we have detected every single one of these license plates. So the only thing we need to do is to take a look what's the license plate we have detected with the highest confidence, and that's it. That's going to be our criteria to know what's the license plate number of this car, and that's it. That's the way we are going to solve our problem, and that's exactly where the object tracking is involved, and that's exactly why it's so important to track, to implement an object tracking algorithm into this problem, because this is how we are going to solve this problem. This is going to be our criteria to select the license plate number for every single car in this video. So remember, we have these two problems. This is how we are going to solve this problem, and then we still have this other problem, which is that we have some missing frames for every single car, right? This problem actually is not really a big problem, and the only thing it's going to affect is the visualization, right? Because now we are going to take all this information and we are going to visualize this information. So The only thing is going to happen with all these missing frames is that we are just not going to visualize the license plate, and we are not going to visualize the license plate value for that given frame. So let me show you what happens if we visualize, if we create a video from the text file, the CSV file I just showed you. We will have a visualization which looks like this, which will be okay, I guess, but it's like it's not an ideal visualization, right? It's like it's not really pretty, it's not really good looking. This doesn't really look good. Ideally, we would like to have a visualization which is more stable. For every single license plate, we would like to see the license plate on a fixed position through all the different frames in which we are detecting the license plate for that car, right? That's exactly what we would expect, and this is not really good looking. This doesn't really look good, right? So in order to fix this problem, which again is not a huge problem and the only thing it does is to affect the visualization, we are going to use one of these two scripts, which is called add missing data. And the only thing this script does is interpolate all of those frames in which we have not detected a license plate, or in which we are not extracting the information for the license plate. So the only thing we're going to do is interpolate the values for the bounding boxes for the car and the license plate in all of those frames. We are going to interpolate the values. And that's it. For example, in the frame number 41, you can see we have the information for the frame number 40, we have the information in the frame number 42, but we don't have the information in the frame number 41. So the only thing the add missing data.py script does is going to consider the bounding boxes for this frame and the bounding boxes for this frame, and it's going to take the average of all the different coordinates, and by taking the average it's going to compute what is the value of the bounding box in the missing frame, right? And it's going to compute exactly the same process in absolutely all the other missing frames. So that's the way we are going to solve this problem, all the missing frames. Remember, this is only a problem of visualization. This is a matter of visualization. It's not a huge problem. And then once we have fixed that issue, then we can just create the video, and that's it. So these two files, I'm going to give you these two files in the GitHub repository of this tutorial. And now let me show you how this works. So the first thing you need to do is to execute add missing data, and you need to change here the path to the file name you are going to interpolate, right? In our case it's test.csv, and then you need to specify what's the file name of the CSV you are going to create with the interpolated data. Let me show you super quickly how this file looks like. I'm going to filter by car ID, and I'm going to select the number 3 again. And you can see that in this case we have computed absolutely every single frame, right? We are starting the number 0 just as before, but now we have computed absolutely every single the values for the bounding boxes for absolutely every single frame until the number 65, which is the last frame in which we have detected this car, right? So this is exactly the data we are creating with add missing data.py. And once we have created this data, this new CSV file, then we go to visualize.py, and then we input something like test interpolated.csv, and then we specify what's the file name of the video we are going to create, in this case out.mp4, and the only thing we need to do is to execute this file, and then to execute this file, and then after a few minutes we are going to have a video which looks exactly like this. And this is going to be all for today. My name is Felipe, I'm a computer vision engineer, and these are exactly the type of videos and the type of tutorials I make in this channel. If you enjoyed this video, remember to click the like button, and also remember to subscribe to my channel. This is going to be all for today, and see you on my next video. So on today's tutorial we will be making an object detection web application. We will be detecting tumors on a brain MRI image. Now let me show you how it works. I'm going to drag and drop an image from my computer. So this is the image we have uploaded, and if I click here on detections, you can see that we have detected 2 objects, we have detected 2 tumors on this image. So this is exactly a project in which we will be working today on today's tutorial. We are gonna make the entire web application using Python and Streamlit, and we're gonna detect objects using an object detector trained with Detectron2. So my name is Felipe, welcome to my channel, and now let's get started. So let's get started with this tutorial, and the first thing we need to do is to create a new PyCharm project. You can see that this is PyCharm, and now let me show you how to create a new project. We need to click here on new project. I'm going to select the directory where I'm going to create this project, which in my case is here, and then I'm going to select tutorial. This is the directory in which I'm going to create this PyCharm project. And then I'm going to create a new environment, and the interpreter will be Python 3.8. Everything else will be just the default values. I'm going to click on create, and that's pretty much all. Now the next step will be to install all the requirements we are going to use today. So I'm going to create a new file which is called requirements.txt. I'm going to name this file requirements.txt. I'm going to press enter, and then I'm going to paste all the requirements, all the dependencies we need to install in this project, which are all of these packages we have over here. So I'm just going to copy and paste these packages over here, and that's pretty much all. Now I'm going to the terminal, and I'm going to press pip install -r requirements, and that's pretty much all. I press enter, and that's going to take care of installing all the requirements. And you can see that I got an error, and basically this error is because we need to install all of these dependencies first, and then we need to install this final dependency, right? You can see that this one is called Detectron2. We need to install everything else first, and then at the end we need to install Detectron2. So I'm just going to comment this line, and then I'm going to press pip install -r requirements again. Okay, now all the requirements have been installed, and now the only thing we need to do is to install Detectron2. So I'm going to uncomment this line, and I'm going to press pip install -r requirements again, and this is going to take care of installing all the requirements. But as we have already installed all these packages, the only one that's going to be installed now is Detectron2. So we need to wait a few minutes. Okay, and that's pretty much all in order to install Detectron2, and now we are all set. All of our requirements have been installed, so it's time to continue. Let me show you how to create a new file. Let's create a new Python file, so we're going to select File, New, Python file, and this file will be main.py. So this is the file in which we are going to be coding the entire web application of today's tutorial. And remember, in this tutorial we are going to be detecting tumors on brain MRIs. So we definitely need an object detector in order to detect this type of objects, right? Let me show you the data I used in order to train this object detector. This is a dataset I found in RoboFlow, and I'm going to give you a link to this dataset in the GitHub repository of today's tutorial, so you can just go ahead and take a look at this dataset if you want to. And this is an object detector I trained using Detectron2. And I'm not going to show you the details of how I trained this object detector, because that's something I have already covered in one of my previous videos. In one of my previous videos, I show you how to train an object detector using Detectron2, and I show you the step-by-step guide. I show you the entire process. So if you are curious to know how exactly I trained this object detector, I invite you to take a look at the video I'm going to be posting over there. And now let's continue. This is the data I used in order to train this object detector, and now let me show you the entire pipeline in which we are going to be working today. Let's get back to PyCharm, and let me show you exactly what are all the steps we are going to be making in this tutorial. The first step will be setting up the title of the web application. So this is the first step in this process. Then the next step is setting up the header, right? The third step will be creating a file widget, upload file, so the user can upload an image about a brain MRI, so we can detect all these objects on top of this image. Then the next step is loading the model, right? Loading the object detector we are going to be using to detect objects. then we are going to load the image the user has uploaded. Then we are going to detect objects, and then the last step in this process will be to visualize the objects we have detected on top of the original image, and we are just going to display this visualization to the user, right? So these are the steps of the entire process, the entire pipeline in which we are going to be working today, and I'm going to show you every single step of this process. So you can see these are 1, 2, 3, 4, 5, 6, 7 steps. In only 7 steps we will have this web application up and running. So let's get started. And the first step in this process is importing Streamlit as st. Okay, then in order to set up the title, I'm going to call st.title, and the title will be something like brain MRI tumor detection. Then in order to set up the header, I'm calling st.header, and this will be something like please upload an image. Okay, then in order to create the file upload widget, I'm going to call st.fileuploader, and I'm going to input 2 parameters. The first one is an empty string, and then it's all the types we support in this widget, and I'm going to say something like PNG, JPG, and then JPEG. Okay, and that's pretty much all. And in order to move one step at a time, let's see if everything executes just fine. I'm going to execute the code as it is so far. So I'm going back to the terminal, and I'm going to type streamlit run main.py. This is going to open my browser, and we are going to see exactly what our web application looks so far. And everything looks just perfect, so we are okay in order to continue. So let's get back to PyCharm, and let's continue with the next step in this process, which is loading the model, loading the object detector we are going to be using today. And remember, we are going to be using an object detector which I trained using Detectron2. And remember, I already showed you how to use Detectron2 in one of my previous tutorials. So let's go back to my browser, and let's see exactly how we can use this model which I trained with Detectron2. Let's go to the GitHub repository of this previous tutorial, and let's see exactly how this training this model, or how using this model, was all about. So I'm going to this file over here, which is predict.py, and this is the file we use in order to load the model, in order to make predictions with a model trained with Detectron2. So the only thing I'm going to do in this tutorial is to copy some of the code in this file, and I'm just going to paste it in the main.py file of our PyCharm project, right? Remember that in this tutorial we are not going into the details of how to use Detectron2, so I strongly recommend you to take a look at my previous video, to take a look at this video over here, which you are going to find in my YouTube channel, so you can see exactly how this using this model, how using Detectron2 works, right? Because we are not going into the details in this tutorial, right? So this is my strong recommendation for you. Please take a look at that previous video. The only thing we're going to do now is just copy and paste some of these lines, which I'm going to explain super quickly. Right? You can see that we are getting a configuration file, then we are getting the weights for this model, and we are getting the weights from this model from our local drive. So we are specifying a file path allocation in our local drive, and the only thing we're doing is specifying the weights location. Then we are creating an object which is our predictor, and this is exactly the model we need in order to continue with this process. So this is a very quick explanation regarding this code we have over here, and now let's continue. Now you can see that we need to make a few imports because we are not finding these objects we have over here, these functions we have. So I'm going up, all the way up, and I'm going to say something like from Detectron2.config import get config, and that should be all for this function we have over here. Then from Detectron2.engine import default predictor, and that should fix this issue over here. And now we need to import from Detectron2 import model so, and that should be all in order to fix this issue over here. I'm going to delete these comments, and that's pretty much all. So everything that's here is everything we need in order to load this model, but obviously we need a model in order to load, right? Because this is just the default code we had in our GitHub repository. So let me show you exactly where it's my model in my local drive. If I go to my file system, you can see that I have this file over here, which is model.pth, and I have this other file, which is label.txt. This is the model we need, model.pth. These are the weights of our model. And then what I'm going to do is to copy this file, and I'm going to paste it in the directory of this Python project, right? You can see that this is the main.py in which we are currently working in. This is the requirements.txt file we created a few minutes ago, and this is exactly where I'm going to paste this model. And I'm going to do something else, which is creating a new directory, which is called model, and this is where I'm going to put the model, and everything it's okay. And remember, I show you we had another file which is all the labels we are detecting, but in our case this is a very dummy labels.txt file because we only have one category. We are only detecting one class, which is tumor. And a very quick note is that remember the dataset I used in order to train this object detector. In this dataset we had two classes which were negative and positive, and this is something like two different types of tumors, or that's what I think. But what I decided to do when I was training this object detector was merging these two labels, these two categories, into only one object, and I called this only one object. I call it tumor, right? So that's exactly why we have only one class over here, given that although the original dataset I used had two categories. So that was a very quick note regarding the model I trained, and now let's go back to my file system. We are not going to use this directory anymore. I go to model, and this is the model we are going to be using. This is the weights, the model weights we are going to be using. So remember, this is within another directory which is called model. I go back to Python, and the only thing I'm going to say is something like model, and then the name is something like model.pth. Okay, and that's pretty much all. In my case, I'm going to run this code in my local computer, which is using a CPU. So this is what I need to specify. If your computer or the computer where you are running this code has a GPU, then the only thing you need to do is to comment this line, and everything will run on your GPU. But in my case, I'm going to run it locally on my CPU, so I'm just going to leave this line as it is. Now let's continue. Now it's time to load the image we are going to use in order to detect all these objects. So this is what I'm going to do. If file, I have to make another edit. So we are uploading a file, and we are calling the file the user has uploaded. We are calling this object file. So now if file, so if the user has uploaded something, we are going to continue, and we are going to call the image. We are going to call this object, we are going to call it image, and then image will be image.open file, and then something like 2RGB, right? An image is an object we are going to import from pillow, right? From pill import image. Okay, that should be all. Okay. Now, in order to move one step at a time, let's go back to my browser and let's see if everything executes just fine. I'm going to refresh, and everything is just fine. And now I'm going to select an image. Let's see everything's okay. The data I'm going to use, it's located over here. This is train and val. I'm just going to select a random image, which is this one. And let's see what happens. We have an error because this is not called to, but this is called convert, if I'm not mistaken. Let's see now. I'm going to refresh, and I'm going to do the same process again. I'm going to select the same image, and I'm going to drop it over here, and you can see that now we have another error because it's not convert, but it's convert. I had another typo. Okay, now let's see what happens. I'm going to refresh again. Let's hope everything is okay now. I'm going to take the image, I'm going to drop it here, and let's see what happens. Now we have to wait a couple of seconds. We may be loading the model, so this may take a few seconds and everything is okay. We are not visualizing the image, so if we are not getting any error, that means everything is okay. So let's go back to PyCharm. Everything is okay so far, and now it's time to detect objects. We are moving super quickly. We are almost there, right? We have almost completed this process, this pipeline, and the only thing we need to do now is to detect objects. And in order to detect objects with this model, which was trained with Detectron2, I'm going back to my browser and to this repository, because let's see exactly how we can make this prediction. The only thing I'm going to do is to copy and paste everything that's from here up to here. We don't really need to draw the rectangle, but let's just copy everything. So I'm going to copy, then I'm going to PyCharm, and I'm going to paste it here. We will need to make a few edits, but most of the code will remain the same, right? I'm just going to fit this image over here, because if I go back to my GitHub repository, you can see that this image is actually a NumPy array, right? We are reading this image using OpenCV, so the format is a NumPy array, and we need to input a NumPy array over here. So I'm going to do something like, I'm going to define another variable, which is image array, and this will be NumPy as array image, right? We will need to import NumPy, so I'm going to say something like import NumPy as MP. And that's pretty much all. Now I'm going to input image array, and that should be it. So this is pretty much all. We are going to be detecting all the objects we have. We are going to be returning all the objects we have detected with a confidence value greater than 50%, and other than that, everything is just fine, and that's it. And we don't really need to draw the rectangle, so I'm just going to delete it, and that's pretty much all. So we have loaded the image, we have detected all the objects on top of this image using our model, and now it's time to continue with the visualization. Now we are going to take all the detections, all these objects we have detected, and we are going to draw bounding boxes on top of the image the user has uploaded. So this is amazing because we're moving super quickly, and let's see how we can continue with the visualization. Now it's the time in which we are going to draw bounding boxes on top of our images, and in order to do so, we are going to use Plotly. Plotly is an amazing Python library which I have used many times in my projects. It's an amazing library. You can do some very crazy visualizations using Plotly, some very dynamic visualizations. So this is a very amazing library we are going to use now. And something that's very important is that in my tutorials, we always focus on the computer vision part of the problem, and everything that's related to the visualization is not really that interesting from a computer vision perspective. So what we are going to do now is just taking the code for the visualization, which I have already prepared over here, right? This is a function which is called visualize, and this is a function we are going to use in order to visualize the bounding boxes on top of our images. So please pay attention, please focus, because otherwise you may be lost. Please take a look at what we are going to be doing now. I'm going to the project, I'm going to file, new, Python file, and I'm going to create a new Python file which is called util.py. Then I'm going back to this file I have over here, and I'm just going to copy the entire file. I'm going to press Ctrl C, and then I'm going to press Ctrl B over here. So this is all the code we need in order to do the visualization. Remember, the visualization is very interesting and very important, but it may not be the most interesting thing from a computer vision perspective, and that's why we are not really minding everything that's visualization, everything that's related to how to visualize all these bounding boxes on top of the images. We are just going to use this function, and that's pretty much all. I need to do a few imports, otherwise this is not going to work. I'm going to import Streamlit as st, and that's pretty much all if I'm not mistaken. Yeah. Now let me show you something which is related to all the code I have just copied. You can see that this is the code of two different functions, right? One of them is called visualize, and this is a function we are going to use now in a few minutes in order to visualize all the bounding boxes on top of our images, and the other function is called set background. And this is another function which is only going to make a very small and a very static detail at the end of this tutorial, which is changing the background of the web application, right? This is only a detail. This is definitely not the most important thing from a computer vision perspective, right? This is just changing the background of the web application of the browser. So this is something we are going to do at the end, and this is also in the code I have just copied and pasted into this file. But now let's focus on this other function, which is visualize. You can see that this function receives two parameters. One of them is image and the other one is bounding boxes. And you can see that the images are the input image, and then the bounding boxes are a list of all the bounding boxes in the format x1, y1, x2, y2. So now let's go back to main, because let's see exactly how we can call this function over here. The first thing I'm going to do is from util import visualize, right? Now the function is imported into our main process. And now let's go back here, and then this is where we are going to call this function. Remember, we need to input two parameters. One of them is the image we are going to import, the image we are going to use in order to draw all the bounding boxes, and we need to input the image in the pillow format, and then the other variable is bounding boxes, right? B boxes. And please focus and please pay attention, because we already have a variable which is b boxes. But if we go back to the documentation, you can see that this variable is a list of bounding boxes in the format x1, y1, x2, y2. So this is not the same as this other variable we have over here. Please pay attention, because otherwise it may be a little confusing. So this is what I'm going to do. I'm going to define a new variable which is bounding boxes underscore. This is going to be a list. And what I'm going to do here is just appending the bounding boxes exactly as we need them to be, right? So this is what I'm going to do, and if I go back to util.py, this is exactly what we need to input. Okay, so we have this object over here, and the only thing I'm going to do is to paste this object over here. And I invite you to take a look at this file. I invite you to take a look at this function, visualize, so you can see exactly how it works, and you are going to see exactly we are using the plotly library, and we are calling some functions, and we are doing some stuff which is related to visualization, right? I invite you to take a look at this function. This is going to be available in the GitHub repository of today's tutorial. But now let's continue, and let's see exactly what happens if we refresh this website and if we upload a new image, and let's see exactly what type of visualization we will be getting with this function. So I'm going back to my local computer, to my file system. I'm going to take a random image again, and I'm going to drop it over here. And you can see that now this is what we get, which is exactly the same image I uploaded over here, this image over here. But now we have these two buttons. One of them is original, which means this is the original image we have uploaded, and then the other one is called detections. And if I press this button, you can see that we are plotting the bounding box exactly on top of the tumor of this brain, right? I mean, I'm not a doctor, so I have no idea what I'm looking at. I have the impression this is a brain and this is an MRI, and based on the colors, I have the feeling that this is the issue, right? This is the tumor. So it looks like we have detected exactly what we should have detected, right? But this is the data I used in order to train the model, right? This is the training data. Now let's see if we have exactly the same performance with the data, with an image, in our validation set, right? This is completely and absolutely unseen data from my model. So let's see what happens if I just take a random image like this one. I'm going back here. This is the image I have just uploaded. Remember, now we are taking completely unseen data for my model. And let's see what happens if I move to the other tab, to the other button, which is detections. And we are successfully detecting the bounding box, the object we should be detecting in this image. So everything is working just fine. And in order to make it more challenging and more fun, let's see if we can detect an image with two objects. I know that there are a few, like this one, which has two objects. So I'm just going to drop this image here. And let's see if we can detect both of these objects, both of these issues. And we can see that we can detect both of them. So everything seems to be working just fine. And this is pretty much all in order to set up this web application up and running. You can see that we are uploading images and we are just detecting all the issues in this image, and we are just uploading everything exactly as we should. The only thing I'm going to do now is to use this other function we have over here, which is set background, right? The only thing I'm going to do is to change the background of this web application so we make it a little nicer. And this is exactly how I'm going to call this function. So I'm just going to main.py. I'm going to import from util, import visualize, and then set background. And then I'm going back to my file system. And this is an image I have prepared in order to change the background. It may not be the perfect background ever, but I think it's going to work. We are going to put this background in our web application. So let's see what happens. I'm going to copy and paste it over here. And now I'm going back to Python and I'm just going to call set background, and I'm going to input bg.png. And let's see what happens if I refresh. And you can see that now we have a much better looking background. So everything looks much better now. Now let me open a new image. I'm just going to select, for example, this image over here so we can see how the entire web application looks like with this new background. We have to wait a couple of seconds and now we are getting the image with all the detections on top. So this is going to be pretty much all for this tutorial. This is exactly how you can create an object detection web application using Python and Streamlit, and this is going to be all for today. If you enjoyed this video, I invite you to take a look at other of my previous videos where I show you how to make an image classification web application, and I'm going to be posting a link to this other tutorial over there. So remember, if you enjoyed this video, most likely you will enjoy that video too, because it's exactly the same process and it's a very similar web application. Congratulations, you have completed my course on object detection. My name is Felipe, I'm a computer vision engineer, and this is exactly the type of videos and the type of courses I make in this channel. If you enjoyed this video, I invite you to click the like button, and I also invite you to subscribe to my channel. This is going to be all for today, and see you on my next video.